Okay. Okay. So there was a supply fluctuation at my side. Okay. So due to that, some issue was there. Okay. I think some of the participants have left. Right. So till now, we have identified the alpha equal to 0 instants for the thyristors T1 to T6, right? So now, no, morning was the different problem. Okay. Yes. So now let us discuss the circuit operation. So at this instant, we are applying the gate pulse to thyristor T1, right? So before that, which thyristor was in a conduction mode? It was like a thyristor T6. Okay, strictly speaking, it was like a thyristor T5 and T6 were in a conduction mode. You will understand once we complete one cycle. Okay, because it is a continuous cycle, na? It is a continuous cycle. So suppose at this instant, the thyristor T1 is triggered. At this instant, the thyristor T1 is triggered. So before this instant, it is like a T5 and T6 were in a conduction mode. T5 and T6 were in a conduction mode. Okay, so when T5, T6 were in a conduction mode, so you can check when T5 and T6, when T5 and T6 were in a conduction mode, how the current will be flowing? Current will flow like a VC, T5, load T6, and again back to the VB. Na? Please check. Before T1, which thyristor pair was in a conduction mode? It was a T5 and T6. Okay. Why the T5, T6 was this pair was in a conduction mode? That you will understand after completion of one cycle. Okay. So now T5, T6 are in a conduction mode. So when T5, T6 were in conduction mode, current will be flowing like VC, T5, load, T6, and back to the VB. So what is the V0? V0 is equal to current is flowing from VC to VB. Na? So V0 is equal to VC minus VB. That is nothing but the VCB, right? V0 is equal to VCB. Okay, so it is like before this instant, that is during this instant, means T6 is fired until T1. Okay, it is like in the output, we were having the VCB voltage. So it is like we'll be getting the voltage at the output terminals is like a VCB. VCB is nothing but your dotted green. Okay, dotted green. Till which instant it will continue? Till this instant, because at this instant we are applying the gate pulse to T1. Na? So you can check from T6 instant, T6 triggering instant means here. So this will appear as an output here. So from this point to this point, we'll be having the output as a VCB. VCB. Okay. Next, at this instant, we are triggering the thyristor T1. So once T1 is triggered, or just check at this instant, we are applying the gate pulse to thyristor T1. But please check whether thyristor T1 will be in a forward bias mode corresponding to this instant, or whether it will be in a reverse bias mode. Okay, because before this instant, it is like T5, T6 were in a conduction mode. So when T5, T6 were in a conduction mode, okay, what is the voltage that was appearing at the cathode of thyristor T1? We can check the voltage that was appearing at the cathode of thyristor T1. It is like, if this is VC, definitely this is VC. Na? Same point is connected here. T5 was in a conduction mode. So if this is VC, therefore it is VC. Same VC will appear here. Same VC means here it is voltage is VC. Right? You can check this voltage is VA means here voltage is VA. So when T5, T6 were in a conduction mode, at that time the anode voltage of thyristor T1 is VA, cathode voltage of thyristor T1 is VC. So voltage across thyristor T1 is VA minus VC. So VA minus VC means VAC. Yes or no? It is a VAC. So please check. Yes, at the instant of applying the gate pulse to the thyristor T1, what is the value of VAC? Okay, what is the value of VAC? So at this instant, we are applying the gate pulse to thyristor T1. You can check the VAC waveform. VAC waveform is nothing but this dotted yellow. Na? This dotted yellow is a VAC waveform, right? So here I am applying the gate pulse to thyristor T1 means at this instant. So corresponding to this instant, what is the VAC? It is a positive or negative? VAC is a positive. means definitely our thyristor T1 is in a forward bias mode. So T1 is in a forward bias mode, and if we apply the gate signal, whether our thyristor T1 will turn on or not, definitely our thyristor T1 will turn on, right? So now here, when we apply the gate signal, our thyristor T1 will definitely turn on. Now let us discuss when T1 turns on, what will happen to T5? When T1 turns on, what will happen to T5? Okay, so now you can check. This is VA, means here it is VA. Same VA will appear here now, because T1 is acting as a short circuit. This is VA, means here it is VA. At the anode of thyristor T5, voltage is VC. At the cathode, voltage is VA. Na? So what is the voltage across thyristor T5? It is a VC minus VA. That is the VCA. Yes or no? VCA. Now you can check the voltage VCA. You can check the voltage VCA. Okay. At the instant T1 is triggered. Okay. At the instant T1 is triggered, means T1 is triggered at this instant. And corresponding to this instant, what is the VCA? VCA is nothing but this one. That is the solid yellow. Okay. Solid yellow. So you can check, this is a solid yellow. And corresponding to this instant, it is a negative. Na? So VCA is negative. So VCA negative means what? It is like our thyristor T5 will turn off. Okay, thyristor T5 will turn off. Are you getting the point? So here thyristor T5 will turn off as soon as thyristor T1 is triggered. As soon as thyristor T1 is triggered, thyristor T5 will turn off. Right? So now, yeah, once T5 turns off, it is like T1 and T6 will be in a conduction mode. So when T1, T6 are in a conduction mode, how the current will flow? Current will flow like VA, yes, T1, load, T6, and again back to the VB. In this loop, the current will flow now. VA, T1, load, T6, and back to the VB. So what is the V0? V0 is equal to VA minus VB. VA minus VB means it is a VAB. Na? In the output, we'll be getting VAB voltage. Okay. So in the output, we'll be getting VAB voltage. Now you can check. At this instant, we are triggering thyristor T1. So before this instant, in the output, we were having VCB. Na? So corresponding VCB means corresponding to this instant, VCB was like this. Till this point, it was a VCB. Na? As soon as T1 is triggered, suddenly our output voltage will increase from VCB to the VAB value. You can check, this is a VAB. Na? So sudden increase to the VAB value. And after that, it will continue till we apply the gate pulse to thyristor T2. At this instant, we are applying the gate pulse to thyristor T2. Okay. At this instant, we are applying the gate pulse to thyristor T2. So you can check, this instant is nothing but this instant. Okay. So in the output, we'll be getting which waveform? That is the VAB. So in the output, we'll be getting the VAB waveform. Okay. So from here till this instant, this is a VAB. Okay. This is a VAB. This is a sinusoidal type of waveform. This is a VAB. Right. Next. Now we are applying the gate pulse to T2. Now we are applying the gate pulse to T2. Okay. So check corresponding to this instant whether T2 means at this instant whether T2 will be in a forward bias mode or reverse bias mode. Okay. So you can check before T2 it is like a T1 and T6 were in a conduction mode. Okay. So when T6 is in a conduction mode along with the T1, what is the voltage that will be appearing at the anode of thyristor T2? You can check. This is VB means definitely here it is VB. This is VB means T6 is acting as short circuit means here it is VB. This VB means here it is VB. Okay. So when T6 is in a conduction mode, voltage across thyristor T2 is VB minus VC. That is the VBC. That is the VBC. So please check corresponding to this instant. What is the value of VBC? What is the value of VBC? Check the waveform VBC. VBC is nothing but your solid green. Solid green. So corresponding to this instant means this point, and you can check VBC value is this much. That is the positive value. No? So VBC positive means definitely our thyristor T2 will be in a forward bias mode. And we are applying the gate pulse. So definitely our thyristor T2 will turn on. No? Thyristor T2 will turn on. Now let us discuss once T2 turns on, what will happen to T6? Once T2 turns on, what will happen to T6? Okay. So now we can check when T2 turns on means here it is VC. So definitely here it is VC, here it is VC. Because T2 is acting as a short circuit now. So this is VC. Same VC will appear here. So now what is the voltage that is appearing across T6? It is a VC minus VB. So voltage across T6 is VC minus VB means VCB. So now you can check VCB voltage. VCB voltage. Okay. Corresponding to at the instant of triggering of thyristor T2. At the instant of triggering of thyristor T2, VCB. VCB is nothing but this dotted green. So VCB corresponding to this instant, it is a negative. Na? So VCB negative means your thyristor T6 will be in a reverse bias mode. So that's why thyristor T6 will turn off immediately as soon as thyristor T2 turns on. I am saying as soon as thyristor T2 turns on, your thyristor T6 is turning off. So when T2 turns on, then and only then the voltage across T6 will be VC minus VB. That is the VCB voltage was appearing. Okay. So once T2 turns on, T6 will turn off. So which two thyristors will be in a conduction mode? It is like a T1 and T2. So when T1, T2 are in a conduction mode, current will flow like VA, T1, load, T2, and again back to the VC. So voltage across load is equal to VA minus VC. That is the VAC. Okay. So in the output, which waveform will be getting? That is the VAC waveform. Actually, till this instant, yes, in the output we were having, till this instant in the output we were having VAB means this type of waveform till this. After this, it will suddenly increase to the VAC, na? Right? So there is a sudden increase in the output voltage waveform, right? So it will be suddenly increasing, right, to VAC, and this will continue till T3, till the gate pulse is applied to T3. This is like your, is this color is visible or not? Right? So this is your VAC. This is the VAC. At this instant, we are applying the gate pulse to thyristor T3. Na? At this instant, we are applying the gate pulse to thyristor T3. So as soon as T3 turns on, what will happen? Your thyristor T1 will turn off. You can check. Okay. Check corresponding to this instant. Corresponding to this instant, as soon as thyristor T3 is turned on, what will happen to T1? Okay. So T3 turned on. T3 turned on means here T3 is triggered. You can check corresponding to the triggering instant whether T3 is in a forward bias mode or reverse bias mode. You can check it. Okay. Because T1 is in a conduction mode. Na? T1 was conduction mode. So this is VA means this is VA. So here it is voltage is VA. Na? So voltage across thyristor T3 at the instant of triggering is a VB minus VA. That is the VBA. So you can check VBA voltage corresponding to this instant. Okay. So corresponding to this instant, you can check VBA. That is the dotted black. Dotted black is positive now. So it is like thyristor T3. Yes, it was in a forward bias mode only. So once we apply the gate pulse, thyristor T3 will immediately turn on. So once T3 turns on, what will happen to T1? Let us discuss. Once T3 turns on, so this is VB means definitely here it is VB. It is acting as a short circuit now. So this VB will appear here, right? So what is the voltage across thyristor T1 now? VA minus VB. That is the VAB. Now you can check at the instant of triggering of thyristor T3, what is the voltage VAB? So VAB is nothing but solid black. So you can check corresponding to this instant, VAB is negative. Na? So VAB negative means what? Definitely our thyristor T1 will feel the reverse voltage and thyristor T1 will turn off immediately. As soon as thyristor T3 turns on, your thyristor T1 will turn off, right? So now which two thyristors will be in a conduction mode? T2 and T3. When T2, T3 conducts, output voltage will be, come on, when T2, T3 conducts, output voltage will be which line voltage? Come on. When T2, T3 conducts, in the output, which line voltage will be getting? Yes. Yes, it is a VBC. VBC, VCB, which one? Some are saying VCB, some are saying VBC. T2, T3 are in a conduction mode. Then the output voltage, yes, it is like current will flow from VB, T3, load, T2, and again back to the VC. Na? So current is flowing from VB to VC. So line voltage, output voltage is equal to VB minus VC. That is the VBC. That is the VBC. Because current always flows from point of higher potential to point of lower potential. Na? Right? So point of higher potential to point of lower potential means the current direction is like this. VB, T3, load, T2, and back to the VC. So it is VB to VC current is flowing. So definitely your VB will be more than that of your VC. Okay. So output voltage will be VB minus VC. That is nothing but the VBC. Okay. So in the output will be getting the VBC voltage. Okay. So means after this instant you can check in the output will be getting VBC waveform voltage. VBC voltage is nothing but your, yes, solid green. Na? Solid green. So there is a sudden increase, and after that till this instant it will be same as that of your VBC. Okay, VBC, right? Similarly, what will happen at this instant? We are triggering the thyristor T4. Once T4 is triggered, your T2 will turn off. Okay, then your T3 and T4 will be in a conduction mode. You can check the circuit operation. Okay, And in the output, we'll be getting which waveform? We'll be getting VBA waveform, right? VBA waveform. This will continue till this instant, okay? At this instant, T5 is triggered. Once T5 is triggered, your T3 will turn off. So next, you can check after this instant is like T4, T5 will be in a conduction mode. So when T4, T5 conducts, in the output, you will be getting it is a VCA waveform, okay? VCA waveform. Yes, VCA. Some part of the VCA is here. This is a 2 pi na. So VCA some part is here and remaining part will be here, right? Remaining part of the VCA will be here, right? So till this instant, okay, till this instant, it is a VCA. And after that, it will be again, yes, VCB, right? This waveform is like your, let me write here. This is VBC. This one is a VBA. And this is your VCA. Some part of the VCA, remaining part of the VCA is here, okay? So now you can check here, right? We are getting this type of waveform. We are getting this type of waveform. Means we are having 1, 2, 3, 4, 5, and 6 pulses corresponding to one input cycle. So that's why it is a 3-phase 6 pulse. That's why it is a 3-phase 6 pulse, right? Now you can check, yes, during this interval, which thyristor, sorry, not here, during, yes, from this point to this point, which thyristor pair will be in a conduction mode? At this instant, T1 will turn on. But before this, you can check VCB was there in the output. So you can check when VCB was there in the output, VCB means current was flowing from VC to VB. So when current was flowing from VC to VB, it is like T5 and T6 were in a conduction mode. Na? So it is like here, T5 and T6 were in a conduction mode. From this point to this point, yes, which thyristor pair will be in a conduction mode from this to this? It is a T6, T1. Next, this one is T1, T2. Next, T2, T3. After this, T3, T4. And remaining here, we are having some portion here, T4, T5. And this part is also T4, T5, right? T4, T5. You can check. First, it is T5, T6. Next, T6, T1, T1, T2, T2, T3, T3, T4, T4, T5. Same. Okay. So each thyristor pair is conducting for 60 degree. But whereas each thyristor, you can check each thyristor T1 is there in a conduction mode from this point to this point, na, means for 2 intervals, thyristor T1 is in a conduction mode, na. So each thyristor conducts for 120 degree, but whereas each thyristor pair conducts for 60 degree. Are you getting the point, right? So each thyristor pair, this is for alpha less than 60 degree only we are discussing. Okay. Each thyristor pair conducts for 60 degree, whereas each thyristor conducts for 120 degree. Okay, each thyristor conducts for 120 degree, right? So we'll be getting this type of waveform. Now you can check input is a sinusoidal, but whether the output we are getting is a AC or DC, it is a DC only, na. Output is a DC we are having. Okay, so here you can check, but whether it is a flat DC, no, it is a pulsating DC. Okay, so it is a pulsating DC we are getting, right? So in the continuous cycle, we are getting this type of waveform. In the continuous cycle, we are getting this type of waveform, right? So this is for alpha less than 60 degree. If for load is, as load is resistive, what about the I0 waveform? As the space is not here, okay, sufficient space. So I0 what? I0 will be in phase with the V0 now. We can draw same nature. The only thing is change in a magnitude, right? The change in a magnitude. Okay. This is for alpha less than 60 degree. Now suppose if alpha is greater than 60 degree, then what will happen? Let us discuss. Okay. If alpha is greater than 60 degree, then what will happen, right? So here you can check, or let me first identify. Pi by 3 means alpha 0 no, for T1. So can I say that this indicates your alpha? Yes or no? This indicates your alpha, na? From here to here it is alpha, right? Again, for thyristor T2, alpha 0 means thyristor T2 omega T2 pi by 3. So this is your 2 pi by 3, and here thyristor T2 is triggered. So can we say that this is nothing but your again alpha for thyristor T2? Similarly, you can check this is alpha for thyristor T3. Similarly, alpha for thyristor T4 and so on, right? So on. Next, now we are going to discuss for alpha greater than 60 degree what will happen. Okay, alpha greater than 60 degree. So let me write alpha greater than 60 degree. Same, it is Vs omega t 0, right? Resistive load alpha greater than 60 degree. Alpha greater than 60 degree. So we're having the voltages like yes, here it is a VAB, this is a VBC, here it is a VCA, right? Next, opposite to that of your VCA, we are having a VAC, opposite to that of the VBC, it is a VCB, and opposite to that of the VBC, sorry, VAB, we are having a VBA, right? So these are the 6 line voltages we are having, right? So this point, okay, this is like your pi by 3, this is like a 2 pi by 3, this point is a pi, 4 pi by 3, 5 pi by 3, and 6 pi by 3, that is a 2 pi, right? This is a 2 pi. Okay, so 60 degree I have indicated, right? Now let us find the V0 waveform for alpha greater than 60 degree. Okay, alpha greater than 60 degree. V0, right? So now alpha greater than 60 degree means let us consider alpha equal to 90 degree. Let us consider alpha equal to 90 degree. Consider alpha equal to 90 degree. So if alpha is equal to 90 degree, at which omega t we are supposed to apply the gate pulse to thyristor T1? For thyristor T1, alpha 0 means pi by 3 na? For thyristor T1, alpha 0 means pi by 3. Okay, so pi by 3 plus 90 degree. At this instant, we need to apply the gate pulse to thyristor T1. Okay, so pi by 3 plus 60 means 2 pi by 3, and plus 30 means here, somewhat here. At this instant, we are going to apply the gate pulse to thyristor T1. Yes or no? Right? Similarly, where we are required to apply the gate pulse to thyristor T2? For thyristor T2, alpha 0 means 2 pi by 3. In that, add 90 degree. 2 pi by 3 plus 60 means pi. Plus 30 we need to add. So at this instant, we are applying gate pulse to thyristor T2. Right? Next, similarly, gate pulse to thyristor T3. Pi plus 90 means here. Gate pulse to thyristor T3. Similarly, 4 pi by 3 plus 90. That is a gate pulse to thyristor T4. Next, 5 pi by 3 plus 90. That is a 360 plus 30. That is a 390. 390 means again it is a 30 degree na? After one complete cycle. So here we need to apply the gate pulse to T5. Right? And gate pulse to thyristor T6. It is like a 0 plus 90. So that is a 90 degree. So at this instant, gate pulse to the thyristor T6. Yes or no? Right? So can I indicate this as thyristor T1 alpha equal to 0 degree means this point na? So can I say that from here to here, we are having alpha for thyristor T1. You can check our alpha is now 90 degree. So you can measure this point to this point. What is the angle? These two yellow lines, angle is 60 degree. And again, here we are having 30 degree. So 60 plus 30 means 90 degree. Right? So this is like your alpha. This is like your alpha for thyristor T1. Alpha for thyristor T1. Similarly, we can indicate alpha for thyristor T2, T3, etc. Okay, but not required. Okay. Now let us discuss how we do the waveform. How we do the waveform. Now, at this instant, thyristor T1 is triggered. So before T1, which thyristor pair will be in a conduction mode in a continuous cycle? In a continuous cycle, before T1, which thyristor pair will be in a conduction mode? Come on. Before T1, which thyristor pair will be in a conduction mode? Yes. T5, T6. Yes or no? T5, T6. Good. So when T5, T6 is in a conduction mode, when T5, T6 is in a conduction mode, in the output, which waveform will be getting? When T5, T6 conducts, in the output, which waveform will be getting? It is like VC, T5, load, T6 and VB na. So it is VC minus VB. That is VCB. Yes or no? So in the output, we'll be getting the VCB waveform. Now you can check before this instant, it is like a T5, T6 were in a conduction mode, but we are applying the gate pulse to T6 here now. So from this instant till we apply the gate pulse to thyristor T1, the T5, T6 conducts. Okay. So can I write from this instant? Okay. So here it is. This instant is nothing but this one. From this instant till this instant, actually in the output, yes, we'll be getting the VCB waveform. But now you can check here T6 is turned on. At this instant, T6 is turned on. So from here, we are having T6 plus T5 conduction mode. So T6, T5 in a conduction mode means in the output we'll be getting VCB. So you can check from this point to 2 pi by 3 means till only till this instant VCB is positive, and after that VCB is negative na. So please try to understand what is the meaning of that negative VCB. Let me first indicate here from this point, okay, till this instant we are having in the output VCB, okay. And after this point is nothing but 2 pi by 3. After 2 pi by 3, VCB is negative. So if VCB is negative, you can check the circuit diagram. T5, T6 were in a conduction mode. But if VCB is negative, VCB is negative, then what will happen? VCB negative means VB is greater than VC. Yes or no? VCB negative means VB greater than VC. So if VB is greater than VC, what will happen to T5, T6? You can check VCB negative. So what will happen to T5, T6? So here VCB negative means what? Definitely your current should flow from VB to VC. Current should flow from VB to VC. Okay. So T5 and T6 were in a conduction mode and the voltage VCB is negative, but whether our thyristors will allow, T5 and T6 will allow the current to flow from VB to VC through T5, T6? No, na? Right? VB greater than VC means current VB to VC, it will be possible only when T3 and T2 were in a T3 and T2 will be in a conduction mode. But whether T3 and T2 are in a conduction mode? No. Is this clear? So that's why what will happen? Yes, this negative voltage will not appear in the output side because the thing is, yes, our T5 and T6 will not allow this reverse voltage, will not allow the reverse voltage, right? So the thing is, yes, you can check after this point VCB is negative. The meaning is from this point till T1 is fired. From this point till T1 is fired. Okay, our output voltage will be 0. Whereas if you compare in the previous case, alpha less than 60 degree, in the output voltage we were having only non-zero values. But whereas in this case we are having some zero portion is present. Why the zero portion is present? Because we have increased the value of alpha, and after some instant this VCB is having a negative value. For purely resistive load, you can check for purely resistive load whether our output voltage is negative. Recall, you can recall from single phase rectifier also. For purely resistive load, whether our output voltage goes into the negative values? No, na, right? So output voltage will not, yes, will not having the negative pulse if the load is purely resistive. But if the load is RL, definitely it will be having some negative pulse. Okay, that we will discuss later on. Okay, so for time being here, VCB is negative, so that's why here it will not appear. Okay, it will not appear, right? So now here you can check if VCB negative, and at this instant I am applying the gate pulse to thyristor T1. So what will happen? So VCB is negative. VCB negative means what? This is VC is less than VB means this negative will appear here. So it is like thyristor T5 will be like you're in an off state. Now when T1 is turned on, at this instant we are applying the gate pulse to thyristor T1. So when T1 is turned on, so T1 along with T1, T6 will conduct. Okay. So how the current will flow? Current will flow like, yes, you can check VA, T1, T6, and again back to the VB. Okay, VA, T1, T6, VA, T1, load, T6, and again back to the VB. So in the output, which waveform will be getting? We'll be getting VA minus VB. That is the VAB waveform. Okay. So in the output, we'll be getting which waveform? VAB waveform. So you can check corresponding to this instant. What is the VAB? VAB is this value. And till pi only it is a positive. After pi it is again negative. Na? So we'll be getting in the output VAB. It is a non-zero only till pi. This is your VAB. In the output we'll be getting VAB only till this instant. Right? This is very small pulse you can check. After that VAB is negative. Okay, if VAB is negative, you can check VAB is negative. Okay, so due to that, our thyristor T6 will turn off. Thyristor T6 will turn off. Okay, so now you can check. VAB is negative means what? VAB is a negative, na? VAB is negative, and you can check at the cathode. Okay, at the cathode of thyristor T6, we are having a VB, na? We are having a VB, right? And VAB negative means here VB is greater than VA. Okay, VB is greater than VA, like this. Okay, so now next, if we apply the gate pulse to thyristor T2, what will happen? Along with T2, T1 will conduct. Okay, T1 will conduct. So when T1, T2 are in on state, which output voltage will be getting? Will be getting it as, you can check, when T1, T2 are in on state, T1 and T2, in the output will be getting VA, T1, load T2, and again back to the VC. So VA minus VC, that is the VAC will be getting. In the output will be getting the VAC. So you can check when T2 is turned on now, what is the status of VAC? So at this instant we are turning on T2. So VAC is like this value now, right? Dotted yellow. Okay, so let me indicate here this type of waveform. So we'll be getting VAC. Okay, till which instant it will appear? Till 4 pi by 3 only. Till this instant only will be getting VAC. Similarly, again it is 0. When T3 turns on, what will happen? You can check corresponding to this instant. We are having which waveform? VBC. So in the output will be getting which waveform? VBC. Same repeats. From here you can check VBC is non-zero from will be positive only from this instant to this instant, na, till 5 pi by 3. So this is till 5 pi by 3. This is VBC, na, VBC. Once T4 turns on, in the output will be getting, you can check this waveform. Okay, dotted black. That is the VBA. In the output will be getting VBA, right? This is a VBA. And similarly, you can check, yes, once from this point, that is 0 to this point, it is again 0. When T5 is turned on, again we'll be getting in the output, yes, you can check corresponding to this instant. In the output will be getting this solid yellow, na, that is the VCA. We'll be getting solid yellow, that is the VCA. Yes. From VCA is 0 at pi by 3, and after that it is negative, no? So we'll be getting this type of waveform. So this is your VCA. So now you can compare this waveform, that is for alpha greater than 60 degree, and the waveform for alpha less than 60 degree. Alpha less than 60 degree, you are having a continuously non-zero voltage. Alpha greater than 60 degree, you are having some zero intervals are present. Alpha equal to 60 degree, what will happen? Come on. If alpha is equal to 60 degree, what will happen? Alpha 60 degree means we are, yes, supposed to apply the gate pulse to thyristor T1 at which instant? At 2 pi by 3. Okay. So before that, which thyristor pair will be in a conduction mode? T5, T6. So when T5, T6 is in a conduction mode, in the output will be having VCB waveform, na? Yes or no? So you can check at 2 pi by 3 if I am applying gate pulse to thyristor T1. Okay. So in the output we will be having VCB waveform. It is reaching the 0 value, and at the same instant I am applying the gate pulse to thyristor T1. Okay. So it is like output will not be having the 0 intervals. Output voltage will decrease. It reaches the 0 value, and from the same instant it will jump to the next value, that is the next line voltage, respective line voltage. Okay. So it will not be having the 0 intervals here. But here alpha greater than 60 degree, yes, it will be having a 0 intervals, right? So that's why we are having the boundary between continuous and discontinuous conduction is a alpha equal to 60 degree. Alpha greater than 60 degree is the discontinuous conduction. Why it is discontinuous? Because you can check, if the load voltage is like this, what about the load current waveform? If the load voltage is like this, what about the load current waveform? Load current waveform will be, yes, when load voltage is 0, definitely load current will be 0, na? Resistive load we are having, right? So let me write it as, this is a discontinuous conduction. Discontinuous conduction. Discontinuous conduction. Whereas in the previous case, this is a continuous conduction. Let me write here. Continuous conduction. Continuous conduction. Is this clear? Continuous conduction. Okay. So you can check. That's why we have given the numbering to the respective switches as T1, T3, T5, T4, T6, T2. Then and only then you will be getting the sequence like this. Okay. right? Otherwise it will be different random sequence you will be getting. Okay, so yes, so now you can check corresponding to this instant, that is zero interval na. So can I say that during this interval none of the switch will be in a conduction mode? Because the voltage is zero means what? None of the switch will be in a conduction mode. Yes or no? Right? None of the switch will be in a conduction mode. Similarly, here also none of the switch. Here also none of the switch. Right? Like this. Now here thyristor T1 is in a conduction mode from which point to which point? You can check. T1 is in a conduction mode from here to here, and along with T2 also thyristor T1 conducts na. Right? So like this we are having. So this is for discontinuous conduction. Now let us derive the expressions for output voltage waveforms. Okay, V0 average, V0 RMS, right? So let me write V0 average. Let us first put the heading for alpha less than 60 degree. Let me write V0 average. V0 average. Yes. What is the V0 average for alpha less than 60 degree? Alpha less than 60 degree, we are having this waveform. Corresponding to 2 pi radian, how many pulses we are having? We are having 6 pulses na. So let me write 6 by 2 pi. 6 by 2 pi. Yes, integration. Now you can check. Here VAB is present from this point till this point. VAB is there na. Right? So can I say that this point? Yes, this point is nothing but what? It is like a alpha na for thyristor T1, and it is pi by 3. So can I say that this point is nothing but pi by 3 plus alpha? This angle is alpha, and this omega t is pi by 3. So can I say that this instant is nothing but pi by 3 plus alpha? And what about this instant? This instant is nothing but, here it is 2 pi by 3 and this alpha. So that is 2 pi by 3 plus alpha. So it is integration from pi by 3 plus alpha to 2 pi by 3 plus alpha. Okay. Let me write pi by 3 plus alpha to 2 pi by 3 plus alpha. Pi by 3 plus alpha to 2 pi by 3 plus alpha. During this interval in the output, we are having VAB. What is the expression of VAB? VML into sine of omega t na, into d omega t. So further we can write it as 6 by 2 pi means it is a 3 by pi. Okay, so let me write 3 VML by pi into integration of sine is minus cos na. Limit pi by 3 plus alpha to 2 pi by 3 plus alpha. Pi by 3 plus alpha to 2 pi by 3 plus. Let us write it as 3 VML divided by pi into cos of pi by 3 plus alpha minus cos of 2 pi by 3 plus alpha. Further, can I write it as is equal to 3 VML divided by pi into same cos of pi by 3 plus alpha minus, can I write this cos of 2 pi by 3 plus alpha as cos of pi minus in bracket pi by 3 minus alpha? Yes or no? You can check. Pi minus pi by 3, it is 2 pi by 3 only. Okay. Minus minus plus, so it is alpha. Okay. So further, what is cos of pi minus theta? Minus cos theta, no? So that minus and this minus, it will become plus. Okay. So let me write it as, yes. So therefore, V0 average is equal to 3 VML by pi into cos of pi by 3 plus alpha plus cos of pi by 3 minus alpha. Na? Now can we write this 3 VML divided by pi into cos of a plus b plus cos of a minus b. Yes, it is 2 times cos a cos b na. Cos of pi by 3 into cos of alpha na. So if you check, it is equal to 3 VML divided by pi into, what is the cos of, yes, it is a 0.5 into 2, that is a 1 into cos alpha. Na? This is a cos alpha. So which is equal to 3 VML divided by pi into cos alpha, right? This is your V0 average. V0 average. Is this clear? Right? So next, can we write V0 RMS expression? V0 RMS. is equal to, yes, we are having V0 RMS is 6 by 2 pi, 6 by 2 pi integration from same interval pi by 3 plus alpha to 2 pi by 3 plus alpha, pi by 3 plus alpha to 2 pi by 3 plus alpha. Yes, it is a VML square into sine square of omega t into d omega t, right? To the power 1 by 2 na. So it is equal to 3 by pi na. So it is root 3 into VML divided by root pi into, let me write it as integration of pi by 3 plus alpha to 2 pi by 3 plus alpha. Sine square can be replaced with 1 minus cos of 2 omega t divided by 2 into d omega t to the power 1 by 2. So which is equal to root 3 VML divided by root pi into, we can write it as omega t minus integration of cos 2 omega t. It is a sine of 2 omega t na. So 1 by 2 into sine of 2 omega t divided by 2, right? Limit pi by 3 plus alpha to 2 pi by 3 plus alpha to the power 1 by 2. So which can be written as root 3 into VML divided by root pi into, yes, we can write it as a 2 pi by 3 plus alpha minus pi by 3 plus alpha. So alpha will get cancelled out. 2 pi by 3 minus pi by 3. So it is a pi by 3 na. Minus, now we can write it as a, sorry, I have taken this divided by 2 here na. 1 by 2 I have written, right? Okay. So, yes, 1 by 2 divided by 2 should be there. Okay. So now can we write it as right? 2 omega t by 2, correct na? Yes, omega t divided by 2. Just a minute, let me take these two outside so it will avoid the confusion directly. I'm taking these two outside, so it will be like a divided by root 2 pi. Okay, so divided by 2 will be there, right? So now it is pi by 3 minus sine of 2 omega t. Put the limit here, so it will be like a plus 1 by 2 into sine of 2 into 2 pi by 3 plus 2 alpha. This is the one bracket minus 1 by 2 into sine of this bracket. It is like a 4 pi by 3. Okay, plus 2 alpha na, to the power 1 by 2. Is this clear? Right? So now further what we can do. So therefore V0 average. Therefore V0 average, right? Yes. Is equal to root 3 VML by root 2 pi. Okay, root 3 VML by root 2 pi. Into, yes, I can write it as pi by 3 plus, yes, 1 by 2 into sine of 2 pi by 3. Let me take 1 by 2 also outside. So it is 1 by 2. Let me use curly bracket here. So 1 by 2 into sine of 2 pi by 3 plus 2 alpha. Okay. And here it is a sine of 4 pi by 3, means sine of 240 degree. Okay, sine of 240 degree. And here it is a 2 pi by 3, that is a 120 degree. Okay, so let me write it as a yes, 1 by 2 into sine of this 2 pi by 3 can be written as a pi minus pi by 3. Okay, so I'm writing it as a pi minus in bracket pi by 3 minus 2 alpha. This is the one thing, right? Next, this minus as it is, so this will be minus here as it is, into sine of, so can we write this 4 pi by 3 plus 2 alpha. 4 pi by 3 is nothing but 240 plus 2 alpha na. 240 can be written as 180 plus 60 na, 180 plus 60. So let me write it as pi plus This is 4 pi by 3 plus 2 alpha. Pi plus pi by 3 plus 2 alpha. No? Yes or no? Right? So, right? Yes. So now, okay. It is a VRMS. Right? So now we can write it as is equal to root 3 into VML upon root 2 pi to the power 1 by 2 should be there, right? So into pi by 3 plus I can write 1 by 2 into what is sine of 180 minus theta? You can check sine of 180 minus theta whether it is equal to sine theta. Yes or no? So it is a sine of pi by 3 minus 2 alpha. Okay. Sine of 180 minus theta, it is a sine theta only. Check the sinusoidal waveform. Okay. So it is a sine of pi by 3 minus 2 alpha minus it is sine of 180 plus theta is minus sine theta, na? Right? So let me write it as plus sine of pi by 3 plus 2 alpha. Pi by 3 plus 2 alpha. So can we write it as to the power 1 by 2? So it is equal to root 3 into VML divided by root 2 pi into pi by 3 plus 1 by 2 into, yes, this bracket, sine of a minus b plus sine of a plus b. So it is a 2 times sine a into cos b, na? So 2 times sine of pi by 3 into cos of 2 alpha. So or no, to the power 1 by 2. So these two will get cancelled out. So it is a root 3 into VML divided by root 2 pi into pi by 3 plus sine pi by 3 into cos 2 alpha. Okay. So it is 0.866, that is a root 3 by 2 into cos of 2 alpha to the power 1 by 2. Right? This is your V0 RMS. Is this clear? Right? So V0 RMS. Next, now we know V0 RMS, we know I0 RMS. Further, we can write I0 average, I0 RMS also. I0 average is equal to V0 average by R. Right? I0 RMS, V0 RMS by R. Right? What is the conduction time of each diode? Conduction time of each diode is equal to each diode, sorry, each, not diode, it is thyristor. Conduction time of each thyristor. Yes, it is. Each thyristor is an on state for 120 degree. Na? Okay, so it is a 2 pi by 3 divided by omega. So it is a 2 pi by 3 omega. Right? And conduction of each thyristor pair. Let me write conduction time or conduction angle. You can write conduction angle of each thyristor pair is equal to pi by 3 omega, right? Pi by 3 omega. Further, we can write it as a P0 average, right? You can check here. For this case, I am writing, okay, each thyristor is in a conduction mode for, you can check 60 degree here, 60 degree here. Okay, T1 is in a conduction mode for 120 degree, right? And thyristor pair is in a conduction mode for 60 degree, right? Further, we can write the load power P0 average. Resistive load, it is a V0 RMS into I0 RMS, right? Etc. So this is for alpha less than 60 degree. Now for alpha greater than 60 degree, can we write? For alpha greater than 60 degree. Yes, V0 average. It is equal to, you can check waveform, alpha greater than 60 degree here. Yes, the waveform you can check. We're having 6 pulses na, corresponding to one input cycle. So it is a 6 by 2 pi, right? 6 by 2 pi. 6 by 2 pi. Integration from, yes, this integration is important here. You can check in the output we are getting VAB only during this interval. Na? So what this value indicates, this instant is like, this is your pi by 3 and this is alpha. So can I say that this is nothing but pi by 3 plus alpha? Yes or no? And similarly, what about this one? This is like your pi. So pi by 3 plus alpha till pi. Pi by 3 plus alpha till pi only will it write. Okay. Till pi. Yes, what is value? VML into sine of omega t into d omega t, right? So we can write it as 3 VML divided by pi into integration of sine is minus cos of omega t, limit pi by 3 plus alpha to pi, right? So it is equal to 3 VML by pi into 1 plus cos of pi by 3 plus alpha. Yes or no? This is your V0 average. Next, further we can write V0 RMS. Same 6 by 2 pi. Integration from pi by 3 plus alpha to pi only. VML square into sine square of omega t into d omega t to the power 1 by 2. Na? So you can check it is equal to 3 into, sorry, root 3 into VML divided by root pi into, we can write integration from pi by 3 plus alpha to pi. Sine square can be replaced with 1 minus cos of 2 omega t divided by 2 na, into d omega t to the power 1 by 2. So which can be written as root 3 into VML divided by root 2 pi into, this is like a omega t minus sine of 2 omega t divided by 2, limit pi by 3 plus alpha to pi to the power 1 by 2, right? So therefore we can write V0 RMS. Yes, so now V0 RMS is equal to root 3 VML by root 2 pi into pi minus pi by 3 minus alpha. Okay, so it is 2 pi by 3 minus alpha. Next, we can write, you can put the limit here, sine of 2 pi by 2, sine 2 pi is 0. Okay, so plus sine of 2 pi by 3 plus 2 alpha na, divided by 2. So we'll be getting this type of expression. Okay, this type of expression, right? So this is the V0 RMS, right? So you can check here, put the limit, right? 2 into pi by 3 plus alpha. So 2 pi by 3 plus 2 alpha, right? To the power 1 by 2. This is your V0 RMS. Okay. Similarly, we can find I0 average, I0 RMS, right? Load power, etc. Now let us discuss the operation of, yes, RL load. Three-phase full wave controlled rectifier with the RL load. RL load. Now we are having the RL load. Same circuit diagram. A, B, and C, right? So this is VA, suppose this is VB, and here it is VC. T1, T3, T5, T4, T6, T2. Okay. So T4, T6, T2. Okay. So R here. This is your V0 and this is a I0, right? V0 and I0. Now, so in this case, again at a time two thyristors will be in a conduction mode, same as that of the previous case, whatever we discussed. Okay. So now here okay, so here again we're having a supply voltage is same as that of the line voltage. Okay, this is your VAB, this is a VBC, and here it is a VCA. Let me write it as a VAC, this is a VCB, and here it is a VBA. Okay, VAB is VML into sine of omega t. VML into sine of omega t. Right, now we are going to discuss the V0 waveform. I0 waveform is a constant current only. Okay, I0 waveform is a constant current only. This is like pi by 3, 2 pi by 3, pi, 4 pi by 3, 5 pi by 3, and 2 pi. Okay, and 2 pi. Right. So we'll discuss only for alpha greater than 60 degree. Okay. For alpha less than 60 degree, it is same as that of the previous case. Okay. Only thing is alpha greater than 60 degree, it will be different. Okay. So let me write alpha greater than 60 degree. So again, let us consider that value, whatever we discussed, that is alpha equal to 90 degree. Alpha equal to 90 degree. So if alpha is 90 degree means where we are supposed to apply the gate pulse to thyristor T1 here, na? Right? Gate pulse to thyristor T2 at this point. Let me show here. Get pulse to thyristor T3. Get pulse to thyristor T4. So it is T1, T2, T3, T4. Similarly, get pulse to thyristor T5. And similarly, the get pulse to thyristor T6. So it is T6. Okay. So this type of triggering we need to apply. Okay. So here T1, T2, T3. So for T1, if you check what is the firing angle, yes, we need to measure from this point. This is pi by 3 means alpha 0 no for thyristor T1 from this point to this point. Okay. So this is the alpha for thyristor T1. Now let us discuss what will happen. Before T1, which thyristor pair will be in a conduction mode? It is a T5, T6. Okay. When T5, T6 conducts, the output voltage will be VCB. Na? Output voltage is equal to VCB. So let me write here. When T5, T6 conducts, the output voltage will be VCB. Here T6 is turning. Here the T6 is turning on. So after this point, it is like T6 and T5 will be conducting. Okay. So you can check from this instant in the output will be getting as a VCB. So from this point till 2 pi by 3, it will be positive only. But after 2 pi by 3, what will happen? As the load is RL, na? Load is a RL now. So what will happen? Our load inductor releases the energy, right? Our load inductor releases the energy through the same thyristor pair. So please try to understand. Let us discuss this circuit diagram. Yes, as I said, T5 and T6 were in a conduction mode. Current was flowing like VC, T5, load, T6 and VB. So V0 is equal to VC minus VB. That is the VCB. V0 is equal to VCB. Okay. It is like load inductor was storing the energy. After, yes, after this instant, you can check after 2 pi by 3, VCB is negative. So VCB negative means what? Yes, your voltage VB is greater than VC. But even though the VCB is negative, but you can check the VCB waveform. You can check the VCB waveform. So corresponding after this instant, VCB is negative. Okay. But near to the 2 pi by 3, VCB value is comparatively less. So here, due to the inductor, what will happen? Our inductor will continue. Our inductor will continue, go on releasing the energy. Our inductor will continue, go on releasing the energy through thyristors T5 and T6 only. Through thyristors T5 and T6 only. Are you getting the point? Okay, means initially current was like VC, T5, load T6, and again back to the VB. So now again inductor will release the energy through L, T6, VB, VC, and again back to the T5. Like this, our inductor will release the energy. So when inductor releases the energy, what is the voltage? It is the same as that of your VCB will appear, na? And that VCB is the negative. So even though the VCB is negative, in the output will be getting the negative voltage as it is till the thyristor T1 is fired. Till the thyristor T1 is fired. So here we will be getting the output is a negative. Output is a negative here, right? So this is your VCB. VCB. At this instant, T1 is triggered. Once T1 is triggered, then what will happen? Once T1 is triggered, in the output will be getting VAB. Na? We'll be getting the output voltage is VAB. Means suddenly the output voltage will increase from zero value. Suddenly the output voltage will increase from this negative value to this positive value. And after that, till pi, we are having the VAB is positive. VAB is positive. After that, VAB is negative, but till we apply the gate push to thyristor T2, our inductor releases the energy through the same thyristor. So that's why we'll be getting the output voltage is like this. Okay, so it should be like this only. This type of waveform will be getting. Okay. So here it is like this. Here T2 is fired. Once T2 is fired, in the output we'll be getting which waveform? VAC. We'll be getting the VAC waveform. Yes. So that's why this type of waveform we're getting. You can check VAC waveform, right? It will be 4 pi by 3 till 4 pi by 3 it is positive, and after that it is again negative. After that it is again negative. Again, when T3 is fired, in the output we'll be getting VBC waveform. Okay, we'll be getting VBC waveform. Yes, so let me indicate VBC waveform. Yes, so here VBC waveform. And next VBC also you can check till 5 pi by 3 it is positive, after that negative. So same, again inductor releases the energy, so again we'll be getting the negative cycle. And at this instant T4 is fired. Once T4 is fired, in the output we'll be getting VBA. We'll be getting VBA like this. So same pulse here, remaining pulse will be here. Okay, remaining pulse will be here. And at T5 is fired, in the output we'll be getting VCA waveform. We'll be getting the VCA waveform. Same here, positive, and after that some negative, and again the same repeats. Is this clear? Right, so it is VCB. After that we are having a VAB. Let me write here VAB. Next to that we are having VAC. Next to that we are having VBC. Next to that it is a VBA. After that it is a VCA, and so on. You can check again, we are having the 6 pulses. Okay, corresponding to one input cycle, in the output we are having the 6 pulses. Is this clear? So here, if the load is RL load, your conduction is a continuous only. If the load is RL load, conduction is a continuous only. Is this clear? Right? So now, what about the I0? I0 is a constant current, na? I0 waveform, if you recall. Yes. So I0 waveform, if you check, it is a constant current. I0 waveform is a constant current. This is a I0. Now, can we draw the waveform of IA? Can we draw the waveform of IA, phase A current? Yes. Let us check the circuit. Yes. So here, let us first write which thyristor pairs will be in a conduction mode. Okay. Here T1 is triggered. So from this point to this point, which thyristor pair? Here it will be T1 and T2 now, right? Next, from this point till this point, which thyristor pair? T2 and T1 and T6 here. T1 and T6. Here T2 is fired, so it is T1 and T2 will conduct here. Next, from this instant to this instant, which thyristor pair conducts? T3 is triggered, so T2 T3. Okay, T2 T3. Next, you can check here. 50% part, remaining part is here. Okay, which thyristor pair is here? T4, and along with T4 T3. So it is T3 and T4. Same here and same here also. T4 and T3. Next, here which thyristor pair will be in a conduction mode? T5 plus T4. T4 and T5. Okay, and after that, you can check here. We'll be having the T6 and T5. T6 and T5 will be in a conduction mode, right? Now from this, our task is to find the IA waveform. Okay, IA waveform. So for that, let us consider this circuit. IA means this current I am saying, right? IA means this current, right? So we can draw for IB also, we can draw for IC also, doesn't matter, right? Now you can check when T1 is in a conduction mode, when T1 is in a conduction mode, whether IA will be positive or negative. When T1 will be in a conduction mode, IA will be positive or negative. Come on. Positive only, because you can check when T1 is in a conduction mode, current is flowing like a T1, like T1 will conduct along either T2, T1 will conduct either with the T6. Okay, so conduction will be either T1 T2 or T1 T6, doesn't matter. But when T1 is in a conduction mode, our IA current will be positive only, right? IA current will be positive. So let me write it as IA is equal to plus I0. And one more thing, we're having the load current is constant now, so that's why it is a plus I0 only, because the same current is flowing through the load. Same current is flowing through the load. Is this clear? Are you getting the point? Okay, so yes. So when T1 is in a conduction mode, IA is equal to plus I0. Now my question is, when T4 is in a conduction mode, what about the IA? Please check the circuit operation. T4 anode is here, cathode is here, na? And we know thyristor allows current in only one direction, that is from anode to cathode. So when T4 is in a conduction mode, IA should be negative, na? Means from T4 the current will be reaching towards the approaching the terminal A. That is nothing but your current in this branch. In this branch, I am saying current in this branch is from right to left. Yes or no? So when T4 is on, IA will be equal to your minus I0 only. Is this clear to all? Please try to understand. Suppose T1 and T2 are in a conduction mode. Let us consider T1 and T2 are in a conduction mode. How the current will flow? Current will flow from VA, T1, load, T2, and again back to the VC. Load current is a constant current we are having. Load current is a constant current we are having. Okay. So now can I say that when T1 and T2 are in a conduction mode, IA is equal to plus I0? Yes or no? Similarly, you can check, suppose T1 and T6 are in a conduction mode. Current will flow from VA, T1, load, T6, and again back to the VB. So when current is flowing from VA to VB, IA will be again I0 only, that is a positive. Next, you can check when T4 is in a conduction mode. T4 will conduct along either with the T3 or T4 will conduct along T5. Yes or no? You can check the circuit. You can check the conduction. Here we're having T4, T5. Here it is T3, T4 na. So T4 is conducting either with the T5. T4 is conducting either with the T3 or T5. Whether T4 is conducting with the T2? No, because you can check T2 and T4 are the lower groups na. Right? So that's why T4 will conduct either with T3, T4 will conduct either with T5. So suppose when T3, T4 are in a conduction mode, how the current will flow? Current will flow like VB, T3, load, T4, and again back to the VA. So current is flowing from VB, T3, load, T4, and back to the VA. I am saying back to the VA means what? Current IA is negative here. Current IA is direction is reverse, na? Right? So that's why IA is minus I0. So please keep it in mind. Okay. When T1 is in a conduction mode, IA is I0. When T4 is in a conduction mode, IA will be minus I0. Now from these two terms, now we are going to draw the waveform of the IA. We are going to draw the waveform of IA. Yes. Do you want to ask something?
No, sir.
Okay, okay, okay. Then please don't raise the hand. Okay, yes. So now, is this clear to all? Right? Is this clear? Okay. Now, here, when T1 is in on state, IA is plus I0 and T4 on state, IA is minus I0. So from this, we need to draw the waveform of IA. Okay, IA we need to draw. Now you can check here. We're having T1. We're having T1 is in a conduction mode from this point till which instant? Till this point. Na? Okay. So what this point indicates? Can I say that this point is nothing but your pi by 3 plus alpha? Okay. And what this point indicates? T1 is the conduction mode from this point to this point. Na? So it is like a pi by 3 plus alpha plus this point. And what this point will indicate? You can check this point is nothing but this is pi by 3. This angle is our alpha is 90 degree. Na? So from this alpha 90 degree means this instant. We can say alpha. And this point is like your pi. Yes or no? So pi plus alpha. Pi by 3 plus alpha to pi plus alpha. Please try to understand. We have considered a alpha is a 90 degree here. We have considered a alpha is equal to 90 degree. So please check if this is alpha. So therefore we need to consider till this instant means before this we need to consider the 90 degree, right? This pulse is 60 degree plus 30 degree, that is a 90. Okay. So it is pi. This instant is pi. Pi plus alpha. So let me write pi by 3 plus alpha to pi plus alpha. Pi by 3 plus alpha, let us consider here it is a, let me write it as pi by 3 plus alpha. Also let me write here it as a pi plus alpha. This is the conduction of thyristor T1. When T1 is in a conduction mode, IA will be plus I0. Na? IA will be plus I0. Right? Next. So you can check here. During which interval T4 is in on state? T4, you can check T4 is here present. Okay. And also T4 is present here. Okay. Means continuously this interval and as well as this interval variable. Okay. So now you can check what this interval indicate. This instant is like, you can check this instant is like, this is 90 degree. Na? 90 degree alpha we have considered. So it is like, let me indicate here. Yes. This will be your alpha now 90 degree. Okay, this is 60 degree plus 30 90. So this point is like 4 pi by 3. Okay, 4 pi by 3 plus alpha. You can check here. 4 pi by 3. This is pi plus alpha, that is 3 pi by 3. 4 pi by 3 plus alpha. Let me indicate here. Four pi by 3 plus alpha till which instant it is present? 4 pi by 3 plus alpha till here continue, na? Right? So you can check this instant is like from here till here. Na? So it is 30. This is 60. This is 90. Okay. So it is like a 2 pi plus alpha. 2 pi plus alpha. Yes or no? So 4 pi by 3 plus alpha to 2 pi plus alpha. So 2 pi plus alpha is somewhat here. Let me write here 2 pi plus alpha. So this is negative. You can check as we discussed. Each thyristor conducts for 120 degree. You can check the difference. Pi plus alpha minus pi by 3 plus alpha. What is the difference? 120 degree. 2 pi plus alpha minus 4 pi by 3 plus alpha. 2 pi is 360 degree. 4 pi by 3. 4 pi by 3 is like your 4 into 60. That is a 240 degree. So what is the difference between 360 and 240? 120 degree. Okay. So this value is a minus I0. But in the continuous cycle, what will happen? Suppose if this is a 2 pi, na, then corresponding to alpha will be having this negative pulse here. Okay. In the continuous cycle, we'll be having the negative pulse here like this. Actually, we have considered alpha bigger angle, so that's why it is creating some problem, right? But please keep it in mind. We are having each interval is of 60 degree like thing. Okay, each interval is of 60 degree. Okay, and when T1 is in a conduction mode for 2 intervals, after that we are having a gap of 1 interval. Na? Next, again T4 conducts for 2 intervals, and again there is a gap of 1 interval. Okay, means when T1 conducts for 120 degree, after that a 60 degree gap is there. Next again T4 conducts for 120 degree, again a 60 degree gap is there. Okay, so same thing is here. We're having a gap here present. Okay, and the important thing, this gap and this gap, this should be same actually. Okay, this should be same, right? So let me draw here. This gap should be same. Okay, so it is like this. Let me consider this point, and here it is this point. Okay, so it is pi by 3 plus alpha, and this point is pi plus alpha. No? This value is I0. I0 here plus I0, right? Now, yes, either you can consider integration from 0 to 2 pi, or you can consider integration from alpha to 2 pi plus alpha. Doesn't matter. Okay, right? So this is the waveform of IA. This is the waveform of IA, right? Now, from this, can we find the IA RMS? Yes, IA RMS. Let me write. IA RMS is equal to yes, IA RMS. Yes, it is 1 by 2 pi. One more thing, RMS either I can find on half cycle or on full cycle. We'll be getting the same value. Okay, so it is a, let me write it as 1 by 2 pi. I'm finding over a full cycle. Integration from, yes, it is like a alpha to 2 pi plus alpha. Let me write it as alpha to 2 pi plus alpha. If you want, you can write for 0 to 2 pi also, doesn't matter. You will be getting the same answer. Okay, it is IA into d omega t, sorry, square to the power 1 by 2, square root of mean of squared value, right? So it is like a 1 by root 2 pi, okay, into, we can write IA alpha to 2 pi plus alpha. We're having two intervals, pi by 3 plus alpha to pi plus alpha. Okay, so integration from pi by 3 plus alpha to pi plus alpha into I0 square into d omega t, plus integration from, you can check, 4 pi by 3 plus alpha to 2 pi plus alpha. 4 pi by 3 plus alpha to 2 pi plus alpha. It is a minus I0 bracket square into d omega t to the power 1 by 2, right? So we can simplify it. I0, we can take I0 square outside. So it is I0 divided by root 2 pi into, this will be like a pi plus alpha minus pi by 3 plus alpha. Alpha cancel out. Pi minus pi by 3, it is a 2 pi by 3. Plus, you can check 2 pi plus alpha minus 4 pi by 3, right? Plus alpha. Alpha cancel out. 2 pi minus 4 pi by 3. So it is again 2 pi by 3 to the power 1 by 2. So you can check it is equal to IA RMS. So therefore IA RMS is equal to, it is a 4 pi by 3. Okay, I0 upon root 2 pi into 4 pi by 3 to the power 1 by 2. So you can check root pi cancel out. Okay, so we can write it as under root 2 by 3 into I0. This is your IA RMS. IA RMS, right? IA. Is this clear? So IA RMS is root 2 by 3 into I0, right? So similarly, we can find IT1 RMS also, right? For IT1, yes. Now, how will be the waveform for IT1? Come on. How will be the waveform for IT1? Thyristor T1 current waveform I want. Thyristor T1 will be in a conduction mode from pi by 3 plus alpha to pi plus alpha. So during that interval, what is the IA? Na? That will be your IT1 waveform. For remaining intervals, IT1 will be 0, na? Yes or no? Right? So let me draw the waveform of IT1 also, and after that we'll stop. IT1 waveform. Yes, it is a pi by 3 plus alpha to this instant. This instant is like your pi plus alpha. This is your IT1, right? This value is a I0, right? We can find the IT1 RMS also, right? That is a 2 pi. Yes or no? You can find IT1 RMS, which is equal to 1 by 2 pi integration from pi by 3 plus alpha to pi plus alpha I0 square into d omega t to the power 1 by 2. So it is equal to, we can write I0 into under root 1 by 3. Okay, it is 120 degree out of 360. So that is under root 1 by 3, right? Right? So this is the IT1 RMS. So these type of questions they have asked, okay, and specifically they ask the IT1 RMS or IA RMS for I0 for RL load where the load current is constant. In that case, actually, generally they have asked previously in number of examinations, right? These type of questions, right? Okay, so we'll take a break here, and after the break, we'll discuss how to find the input power factor. Okay, for three-phase full wave rectifier with a highly inductive load, right? Because if you check for highly inductive load, we are having the source current is a non-sinusoidal, no? So how to find the input power factor, that we will discuss, right? Okay.
Sir, in 88,
Shall we discuss it at the end?
sir, only correction is there.
Yes,
88.
please.
Sir, conduction angle you said and YU divided by
Okay,
omega.
okay. Sorry. That should be pi by 3 only, right?
Ha. Yeah.
Okay. Thank you. Okay, we'll start at 7:35, right? Okay. Yes. So now let us discuss the input power factor expression in the case of three-phase full wave controlled rectifier, okay, with RL load or RLE load, highly inductive load current is constant. Okay, so input power factor for RL load or RLE load, right? Highly inductive load, right? I0 is equal to I0. I0 is equal to I0, right? So now, just now we have drawn the waveform for the source current. Yes or no? This is the source current waveform we have drawn, right? So let me copy it. Okay. Yes, this is the waveform we are having for the source current. Now, always keep it in mind, when the input power factor is required to be calculated for three-phase rectifier. Okay, three-phase rectifier means where the input supply is a three-phase, na, right? Then we need to find the input power factor for highly inductive load. We discussed it is a DF plus DPF. Okay, but here while finding the input power factor, whereas in a single phase, if you compare, there we had only single phase input voltage, okay, that is a Vs, and only one current was there, na, that is a Is. But here we are having a three phase voltages and three line voltages, right? Or you can say the six line voltages we are having, and we are having the three currents also, na, supply. So here, while finding the input power factor, we need to consider the phase voltage, input phase voltage, okay, and one line current relation. Okay, input phase voltage we need to consider, means either you can consider VA or VB or VC. Okay, if I consider VA, then I need to consider the current, okay, is equal to IA. Then I need to find, then we need to find the input power factor. Okay, so here it is not like the voltage is line voltage. No, here we need to consider the voltage is a phase voltage. We need to consider the voltage is a phase voltage. Please note it, right? Now, because what the DPF is nothing but what? It is a displacement power factor. It is a cosine of angle between voltage and current, na? Then which voltage we need to consider here? We need to consider the phase voltage, okay? And which current we need to consider? That respective line or the phase current we need to consider. Okay, so now, yes, so here input power factor. So we're having the waveform for IA, this one. Just before the break we discussed this waveform, right? Now you can check, this is a Cauchy square wave, this is a Cauchy square wave. By observing this waveform, yes, we can say that it is neither even nor odd. Yes or no? This waveform is a neither even nor odd waveform. Okay, so in order to bring it into, yes, in the odd waveform, yes, in the odd waveform form, yes, what I am going to do, I am going to shift this waveform by angle 30 degree, by angle 30 degree to the left hand side. Okay, so same method I am using whatever we used in the single phase. Okay, whatever we used in the single phase. So if I shift this waveform by 30 degree, if I shift this waveform by 30 degree, okay, so it is like this pi by 3 will start here at, that is a pi by 6 plus alpha. Yes or no, right? So we'll be having like this. Let me, yes, draw here and indicate that current as a IA dash. IA dash. Consider alpha is a general here, right? Consider alpha is a general. Okay. So this is the 2 pi we're having. So pi by 3 instead of pi by 3 plus alpha, now it will be starting at a pi by 6 plus alpha. Pi by 6 plus alpha, and it will be ending at instead of pi plus alpha. Okay, it will be till pi minus pi by 6. Okay, pi minus pi by 6. So it is like 5 pi by 6, right? So it is a 150. 5 into pi by 6 plus alpha. During this interval, we are having it is a I0, right? Next, instead of 4 pi by 3 plus alpha, that is a 4 pi by 3 plus alpha minus 30 degree. Okay, so I think it will be starting at 4 pi by 3 means 240. 240 minus 30, that is a 210. 210 means it is a 7 pi by 6, right? 7 pi by 6 plus alpha, right? And till which point, instead of 2 pi, okay, instead of 2 pi, it will be ending at 2 pi minus 30, that is a 330. Okay, let me write for 2 pi only I am considering. So it is a 330, that is 11 pi by 6 plus alpha, right? So 11 pi by 6 plus, and plus this till 2 pi, it will be 0. I'm shifting this with 30 degree. I have shifted this waveform to the left hand side by 30 degree. Okay, now you can check. Yes, here we are having a 5 pi by 6 plus alpha. So somewhat here we will be having a pi, right? Somewhere here we will be having a pi, right? So now you can check it is 0 to pi by 6 plus alpha. Okay, and here pi, and here it is 5 pi by 6 plus alpha. Okay, 5 pi by 6 plus alpha, right? So here we are having the gap of pi by 6 plus alpha. Next, this pulse is of 120 degree. Next, 5 pi by 6 to 7 pi by 6. If you check, this is equal to 60 degree gap here. Okay, and again the pulse of 120 degree. So 120 plus 120, 240, 240 plus this 60, 300, and the remaining 30 here, and here it is a remaining 30. That is a 360 altogether. Okay, 360 altogether, right? Now, suppose before this zero, which pulse will appear in the continuous cycle? Whatever the pulse we are having from pi to 2 pi, na, that pulse will appear here, na? Yes or no? Whatever the pulse we are having between pi to 2 pi, the same pulse will appear before 0, right? So now you can check if it is 0 to pi by 6 plus alpha. So before 0, yes, 2 pi minus this instant, na, right? So you can check this interval. This interval is like here 2 pi minus pi by 6 plus alpha here. Okay, so this is like your again pi by 6 plus alpha gap is there. So that will appear here pi by 6 plus alpha gap. Okay, so same thing means by you observing this waveform, can we say that it is a even function? Yes or no? Sorry, it is a odd function, right? It is a odd function. Yes. So I am writing IA dash is a odd function. Is an odd function. If it is an odd function, then can I say that an is equal to 0, right? An is equal to 0. I have considered this alpha general thing. Are you getting the point? I have considered alpha as a general thing, right? Okay, so now here an is equal to 0. An is equal to 0. What about the a0 by 2? That is the average value. This is the average value. It is also 0, no? Average value is equal to 0. So a0 by 2 is 0. An is also 0. The only thing is we need to find bn. But now instead of finding the bn general thing, I am finding only b1. I am going to find only b1 because if you check, input power factor is what? df plus df into dpf. For df, what we require? Df means what? It is a ratio of IS1 RMS divided by IS RMS, na? Yes or no? IS1 RMS divided by IS RMS. That is your df. Okay, so we require only fundamental thing. As also, if you check the displacement power factor, for displacement power factor, what we require? It is a cosine of angle between, yes, fundamental source voltage and fundamental source current. That's only fundamental things we require. So that's why, in order to save the time, what I am going to do, I am going to find only b1 value. Instead of bn, I am going to find the b1 value. How to find the b1 value, right? So for those who are preparing for ESE, right, please check how to find the b1 value, because it is required. Okay, while solving your conventional questions. Okay, So it will save your time. Instead of writing the bn full expression, I am going to write the b1 only. I am going to write the b1 only. B1 means consider only n is equal to 1, right? Consider only n is equal to 1, right? We know. So how to write b1? B1 generally for bn, how we write? It is equal to 2 by 2 pi. Na? So same here, 2 by 2 pi. Yes, it is like a integration. Now integration, if you can check, pi by 6 plus alpha to 5 pi by 6 plus alpha. Okay, pi by 6 plus alpha to 5 pi by 6 plus alpha. What is the value? Value is here, this I0, no? This term is I0, this term is minus I0. Okay, so this is I0, this is minus I0. So I can write I0 into what we write? It is into sine of n omega t we write, na? Instead of n, simply put 1. So it is a sine of omega t. So I0 into sine of omega t into d omega t. Yes or no? For bn we write n omega t, right? So here simply replace n with 1. So that's why it is b1, na? So sine of omega t d omega t, right? Plus what we can do, integration from, you can check here, 7 pi by 6 plus alpha to 11 pi by 6 plus alpha. Okay, so 7 pi by 6 plus alpha to what? It is a 11 pi by 6 plus alpha. What is the value? Minus I0 into sine of omega t into d omega t. Now can we simplify it? Yes, it is equal to I0, we can take common. So it is a I0 by pi into, yes, integration of sine of omega t, it is a minus cos of omega t. So minus cos of omega t, limit pi by 6 plus alpha to 5 pi by 6 plus alpha, minus this, minus as it is, and integration of sine is minus cos, so that will be plus cos of omega t into 7 pi by 6 plus alpha, that is 210 degree to 330 degree, that is 11 pi by 6 plus alpha. Yes or no? Now next, let us put the limits. So we can write it as a b1. Therefore b1 is equal to, yes, I0 by pi into, we can write it as cos of pi by 6 plus alpha, cos of pi by 6 plus alpha, yes, minus cos of 5 pi by 6 plus alpha, minus cos of 5 pi by 6 plus alpha. This is the one thing. Next, yes, plus cos of 11 pi by 6 plus alpha plus cos of 11 pi by 6 plus alpha. Next, we can write a minus cos of 7 pi by 6, minus cos of 7 pi by 6 plus alpha. Yes or no? So further we can write it as I0 by pi into, yes, this can be written as cos of pi by 6 plus alpha minus cos of 5 pi by 6 plus alpha, that is a cos of 150 plus alpha. So cos of 150 can be written as cos of 180, okay, minus 30. So cos of pi minus pi by 6 minus alpha I am writing. This is the one thing. Plus this cos of 11 pi by 6 plus alpha can be written as 11 pi by 6 means 330 degree, na? So this can be written as 2 pi minus pi by 6, okay, minus alpha. You can check 2 pi minus pi by 6 means it is a 330 degree, okay, and minus minus plus, so that's why it is as it is, minus cos of 7 pi by 6 plus alpha. 7 pi by 6 is 210 degree. So can we write it as cos of 180 plus 30 degree? Okay, so it is a pi plus, let me write it as 7 pi by 6, okay, plus alpha as it is, okay, cos, sorry, not 7 pi by 6, pi by 6, okay, pi by 6 plus alpha. Is this clear? You can check pi plus pi by 6 means 210 degree, right, as it is, same as that of this. So you can write it as is equal to I0 by pi into cos of pi by 6 plus alpha, cos of 180 minus theta, minus cos theta, that minus this minus, it will become plus. So cos of pi by 6 minus alpha, yes or no, plus cos of 2 pi minus theta, cos of 360 minus theta, it is a cos theta, na? Check the cosine waveform, right? Cos of 360 minus theta, it is a cos theta only. So plus cos of pi by 6 minus alpha minus cos of 180 plus theta. Cos of 180 plus theta is minus cos theta. So that will be plus cos of pi by 6 plus alpha. So now can I write cos of pi by 6 plus alpha, cos of pi by plus 6 plus alpha? It is a 2 times. Cos of pi by 6 minus alpha, cos of pi by 6 minus alpha. It is a 2 times. Okay, so let me write it as, therefore B1 is equal to, yes, I0 by pi into 2 into, we can write it as a cos of pi by 6 plus alpha plus 2 times cos of pi by 6 minus alpha. So therefore, can we take 2 common? Yes, it is a 2 into I0 divided by pi into cos of pi by 6 plus alpha plus cos of pi by 6 minus alpha, cos of a plus b plus cos a minus b. Okay, so it is 2 times cos a cos b. So 2 times cos a, that is cos of pi by 6 into cos alpha, right? So it is equal to 4 into I0 divided by pi into, what is the cos of pi by 6? Yes, it is cos 30. So it is 0.866, right? You can write root 3 by 2 also into cos of alpha. This is your B1. This is the B1. Yes or no? 4 into I0 by pi into root 3 by 2 into cos alpha. This is the B1. So if this is the B1, can I write this B1? We have written for which waveform? IA dash, not for IA. Please be careful. Okay, this is for IA dash. Okay. So now from this, can I write? Therefore, IA1 dash. IA1 dash means what? Fundamental component of the IA dash. Okay. So IA1 dash. Yes, let me write IA1 dash. It is a fundamental component of IA dash. Okay, is equal to what? We know it is AN is already 0, A0 by 2 is also already 0. The only thing is B1 is there. Okay, so it is a B1 into sine of omega t, na? So which is equal to 4 into I0 divided by pi into, let me write it as root 3 by 2 into cos of alpha. So this can be written as, therefore IA1 dash is equal to 2 root 3 into I0 divided by pi into cos of alpha. This is your IA1 dash into sine of omega t, as it is. Sine of omega t. Sine of omega t. Is this clear? This is your IA1 dash. This is the IA1 dash, right? Now, if this is the IA1 dash, can we write IA1? So therefore, IA1. How to find IA1? You can check IA1. IA1 dash and IA1, what is the phasor relation? After shifting IA to the left hand side by 30 degree, yes, we got the IA dash, na? Right? So can I say that, yes, IA is lagging to IA dash, okay, by angle 30 degree. Okay, IA is lagging to IA dash by angle 30 degree. So let me write IA as IA is lagging to IA dash by 30 degree, that is pi by 6, that is pi by 6 radian. Okay, so therefore I can write IA1 means in this we need to replace angle with omega t minus 30 degree. Okay, omega t minus 30 degree. So it is equal to 2 into root 3 into I0 divided by pi, 2 root 3 into I0 divided by pi into cos alpha into sine of omega t minus pi by 6. This is your IA1. This is your IA1, right? Next, now which voltage we need to consider? IA1 is nothing but current flowing through the line A. If you check the circuitry, yes, IA means this current, na? IA means this current we are having. Okay, so which phase voltage we need to consider? We need to consider phase A voltage, na? We need to consider phase A voltage. But we are having these are the line voltages, na? VAB, VBC, these are the line voltages. So what is the relation between line voltage and phase voltage for a balanced system? Yes, can anyone? If you recall, Yes. Suppose if I am having the voltages like, suppose this is VA, this is VB, this is VC, na? Right? So, where will be the waveform of VAB? VAB, this is your minus VB, right? VA minus VB, VA plus of in bracket minus VB is nothing but your VAB. This is a VAB, and this angle is 30 degree. The meaning is your VA is lagging to VAB by angle 30 degree. Okay, VA is lagging to VAB by angle 30 degree. So let me write here. Yes. Phase voltage VA. Phase voltage VA will lag to VAB by angle 30 degree. By angle 30 degree. So therefore, I can write V, because we consider VAB expression is VML into sine of omega t, na? So therefore, it is VA is equal to your VM into sine of omega t minus 30 degree. That is a pi by 6. This is your phase voltage. This is your phase voltage. That is a VA. We need to consider, right? So now if this is the VA and it is a pure sinusoidal, na? So this is equal to your VA1 only. This is equal to your VA1 only, right? This is a phase voltage. Now if this is VA1, this is IA1. Now can we find the DPF and DF, right? DF is equal to DF, distortion factor. Distortion factor is equal to DF is equal to what? IA1 RMS divided by IA RMS, na? What is your IA1 RMS? We have already calculated. IA1 RMS. Yes, here it is. We have represented IA1. Yes, peak value is 2 root 3 into I0 by pi into cos alpha. So what is the RMS value? Root 2 into root 3, na? Right? Means this term divided by root 2. So let me write it as, yes, it is a 2 root 3 into I0, 2 root 3 into I0 into cos of alpha divided by, this is pi. This term divided by root 2 means what? This is your, yes, IA1 RMS divided by, what is IA RMS? If you check the IA waveform, yes, this is our IA waveform, na? We're having the non-zero pulse for 240 degree. Okay, so RMS value is equal to, yes, I'm writing directly. It is a I0 into under root 2 by 3. Right, under root 2 by 3. You can check. We're having 120 positive, 120 negative out of the 360, na? Right? So therefore, RMS value will be I0 into under root 2 by 3. Okay, so this is root 2 divided by root 3, root 2 by root 3. So now from this we can write this root 3. Okay, right? So further we can write it as, just a minute. Yes, this is divided by root 3. So now therefore DF, we can write it as a root 2, means this is a root 6 into I0 into cos of alpha, right? Into this root 3. Okay, will be shifting in the upward direction. Divided by, this term will be like a pi into root 2, na? Pi into root 2. Yes or no? Right? First thing is I have shifted this root divided by root 2 to the upward side, right? That is the numerator side. So this is, this will be root 2 into root 3. That is the root 6 will become there into I0 into cos alpha into this divided by root 3 was there. Okay, and divided by pi into root 2. So now in this you can check here, which is equal to, we can write it as root 6. Right, and one more thing, I0 will get cancelled out. Okay, so this I0 will not appear here. Right, so now you can check here, root 6 into root 3 divided by pi root 2. It is 0.955, 0.955. This is your DF. This is your DF. I'm right. Yes, representing like this. Is this clear? This is the DF you are having. That is the 0.955. Okay. Now, yes, definitely into cos alpha should be there. Definitely into cos alpha should be there. So into cos alpha. Right, same cos alpha will be. Now what about the dpf? Dpf, yes, dpf is equal to, we know it is a cosine of angle between VA1, okay, and IA1, VA1 and IA1. So which is equal to, therefore dpf is equal to, you can check, we are having VA1 expression, we are having IA1. VA1 means it is sine of omega t minus pi by 6. And we have written IA1 is equal to sine of omega t minus pi by 6. So what is the phase displacement? 0 degree. Okay. So can I write it is equal to cos of 0 degree. So it is equal to 1.0. So therefore input power factor is equal to 0.9, or before that df into dpf, df into dpf. So it is equal to, we can write 0.955 into cos alpha, 0.955 into cos of alpha into 1, which is equal to 0.955 into cos of alpha. This is your input power factor, right? Simply you can memorize this expression. Okay, memorize this expression. This is for your full controlled three-phase rectifier. Okay. Yes, so what you are saying here? For half wave, actually the thing is, we don't have the input power factor type thing. You can check in a single phase half wave rectifier also, as well as in a three-phase half wave rectifier also. Okay, we don't have a power factor like thing, because in a half wave rectifier, whether your source current will be having a negative pulse, no, na, right? And this is used only for when your source current is non-sinusoidal, but it is a AC, right? So how the root 2? Yes, this root 2 you are saying, because it is a RMS value, na, means this is peak value divided by root 2 means RMS value, and this peak value is here. Yes or no? Here it is a peak value. You can check IA1. Yes, this is a peak value, na. So I have taken this term divided by root 2. This term divided by root 2. That is nothing but the RMS value. Is this clear? Yes, here we have calculated or derived only the fundamental, and that is what required. That is what required. Is this clear? Right. So this is the final expression. You can simply memorize this expression, right? But derivation in some of the cases, that is the ESE conventional questions type of thing. Okay, you might be required to derive something while solving the numerical, right? So that's why I have given here, right? So for GATE students, it is not required. You need simply you need to memorize this expression. Okay. So this is the input power factor expression. Now we are going to discuss the three-phase semi-converter. Okay, three-phase semi-converter. Yes. Let me put the heading three-phase semi-converter. Circuit diagram. We are almost at the end of rectifier chapter. If you check, very vast contents we are having in the rectifier. Comparatively, your inverter and DC to DC converters. Okay. We are having variety of circuitries. Just a minute. Here it should be diodes. is A, B, C, right? Thyristors are supposed T1, T3, T5. Yes, Vishnu, do you want to say something?
Sir, just one thing, sir. These things we have learned so much this till this point. So when you're studying these units, what are the major things you have to look in? What waveforms you have to look in, and what are the factors we must consider while studying, sir? Like when
Okay,
you're
okay. I will complete it in short. Okay.
Yes, sir.
Okay, okay. So, 462. So this is your freewheeling diode. Next, we are having R and L, V0 and I0, right? So now here we are having semi-converter means out of the 6 switches, 3 are the thyristors and remaining 3 are the diodes. Okay, so 1, 3, 5, these are the thyristors. D4, D6, D2, these are the diodes. Okay, so now, yes, again at a time, yes, we will be having a 2 switches, one from the upper group, second one is from the lower group. Okay, these will be in a conduction mode, right? So means with the T1 either D2 will conduct, or with T1 D6 will conduct. Similarly with T3 D4 will conduct, with T3 D2 will conduct, T5 D6 will conduct, D4 will conduct, like this. Okay, so now in this we are having the 2 modes of operation. One is alpha less than 60 degree, second one is alpha greater than 60 degree. For alpha less than 60 degree, the freewheeling diode will not operate. Okay, but for alpha greater than 60 degree, yes, there will be the functioning of the freewheeling diode. Okay, how we will discuss, right? So yes, here. Yes. So if you check again at a time, 2 switches will be on state, means definitely your source current, yes, supply current waveform is nothing but a 6 line voltage waveform, now 0. This is the omega t, right? So it is, this is like a pi by 3, 2 pi by 3, pi, 4 pi by 3, 5 pi by 3, and here it is a 2 pi, right? Next, we already discussed the what is alpha equal to 0 point. Okay, so here let me indicate. So this is like your alpha equal to 0 for thyristor T1. This is for, now here we are having thyristors, you can check T2 is not there, T1, T3, T5, only 3 thyristors we are having. Okay, so actually 2 pi by 3, it was like alpha equal to 0 for T2. So now for T3 it is like alpha equal to 0 for thyristor T3. Okay, similarly you can check alpha equal to 0 for thyristor T5, it will be here. We are having only 3 thyristors now, so T1, T3, T5, T1, T3, T5. Okay, now let us discuss the circuit operation. First, for alpha less than 60 degree, that is consider alpha is equal to 30 degree. Okay, alpha equal to 30 degree, what will happen? So for alpha less than 60 degree means alpha equal to 60 degree, 30 degree suppose, what will happen, right? So you can check here the V0 waveform I'm going to draw. V0, 2 pi by 3, pi, 4 pi by 3, 5 pi by 3, and 2 pi. Okay, now alpha equal to 30 degree means we need to apply the get pulse to thyristor T1. Okay, at this instant, this is pi by 3, 2 pi by 3, 60 degree. So here I am applying the get pulse to thyristor T1. Get pulse to thyristor T3 at this instant, and get pulse to thyristor T5 at this instant. So here I need to apply get pulse to T1. Here it is T3, and here it is T5. T1, T3, and T5. Right. Next, now you can check once T1 turns on, okay, with the T1, yes, let me indicate the line voltages also. This is a VAB, VBC, and here it is a VCA. Similarly, we are having just like a VCA, it is a VAC, right? Similarly, we are having a VBA, and just like a yes, this VBC, we are having a VCB also, right? So now once T1 turns on, with the T1, actually, which switch will be in a conduction mode? You can check with the T1. Actually, the D6 will conduct now. Recall the previous operation. Okay. So with the T1, actually, D6 will conduct. So when T1 D6 conduct, current will flow from VA, T1 load D6. Yes, VA T1 load D6 and again back to the VB. Okay. So in the output we'll be getting which voltage? It is a VAB. We'll be getting the VAB voltage. Means from this instant we'll be getting the VAB voltage. So here it is like a VAB. Let me write here, indicate here. This is a VAB. I have drawn only till this instant of 2 pi by 3. Why? You will understand. You can check at this instant during this interval. If you check, we're having a VAC at the peak value, na VAC. So you can check VAC. VAC means VA to VC. So during VA to VC, when current flows, it is like VA T1 load D2 and C na VC. So VAC is a peak value, means with a T1 definitely D2 will conduct now, because diode D2 is a uncontrolled device na, right? So if you check initially, definitely with the T1 D6 will conduct, right? With T1 D6 will conduct, and in the output will be getting, it is like a VAB. Okay, VAB. But the next point is, you can check this will continue till only 2 pi by 3, because after 2 pi by 3 VAB is less than VAC. VAB is less than VAC. So as VAC is greater, so definitely with the T1 your diode D2 will conduct. Okay, diode D2 will conduct, means once D2 will turn on, definitely your diode D6 will turn off. Okay, once D2 turn on, definitely your D6 will turn off. You can check just like whatever discussed in the previous. Okay, so this will feel the reverse voltage and it will turn off. Okay, so now with the T1, which diode is in the conduction mode? D2. So when T1 D2 conducts, current will flow like VA T1 load D2 and again back to the VC. In this loop the current will flow. Okay, so output voltage will be getting, it is like a VA minus VC, that is the VAC. Okay, we'll be getting the output voltage is equal to VAC, right? VAC. So initially it was a VAB, after that we'll be getting a VAC. So here it is a VAC we'll be getting. So this is a VAC. Next, now if you check at this instant, omega t is equal to pi is nothing but alpha equal to 0 for thyristor T3, but we're applying the gate pulse to thyristor T3 at this instant. Okay, so till T3 turns on, yes, in the output will be getting only VAC only, right? So let me write here, the VAC waveform will be appearing till the T3 is turned on. So you can check VAC till this instant. So it is like this. Till this instant it will be like a VAC. This type of waveform will be getting in the output. At this instant T3 will turn on. At this instant T3 will turn on. So you can check once the T3 turns on. Once the T3 turns on, so what will happen? So once the T3 turns on, yes, initially T1 D2 were conduction mode. So now T3 is conducting. Once the T3 is turned on, definitely our thyristor T1 will turn off immediately. Yes or no? With the reverse voltage. So with the T3, if you check with the T3, yes, D2 will conduct now. You can check this voltage. Which voltage is peak value? VBC we are having na? Corresponding to this voltage, VBC is peak value. So here with T3, D2 will conduct, current will flow from VB, T3, load, D2 and back to the VC. So output voltage is equal to VBC we'll be getting the output voltage is equal to VBC. So you can check, initially the voltage was here. After that suddenly increase to VBC na? So suddenly increase will be there. And after that it will continue for VBC only till 4 pi by 3. Only till 4 pi by 3 it is a VBC. After 4 pi by 3 what will happen? You can check after 4 pi by 3 VBA is a peak na? VBA is a peak compared to the VBC. VBA is a now maximum greater. Okay, so if VBA is greater, you can check if VBA is greater, definitely T3 is in a conduction mode, but with the T3 diode D4 should conduct. Once D4 conducts, your diode D2 will turn off. Means you can check T3 and D4 conduct. Once T3 D4 conducts, current will flow like VB, T3 load, D4 and again back to the VA. Okay, so voltage across the load will be equal to your VB minus VA. Okay, that is the VBA. Okay, that is the VBA. So you can check this VBA will appear till we apply the gate pulse to thyristor T5. Till we apply the gate pulse to thyristor T5. So let me indicate here. Yes, VBA will appear till this instant. right? So till this instant, it is a VBA. So it will be like this. So you can check, we are getting one controlled pulse and second one is like full pulse we are getting. It is a VBA. At this instant, T5 is turned on. At this instant, the T5 is turned on. Okay, once T5 turns on, that is T5 is turned on, immediately your T3 will turn off, right? Immediately your T3 will turn off. Okay, so with the T5, which diode will be in a conduction mode? T4. So you can check current will flow from VC, T5, load, D4, and again back to the VA. Okay, so current is flowing from VC to VA. So voltage will be VCA, na? Load voltage is equal to VCA. So you can check here. In the load voltage, will be getting VCA. Initially, it is like this. After that, it will be suddenly increasing. Okay, we'll be getting it as a VCA. Let me write here VCA. This will continue till 2 pi. VCA will be there till 2 pi only. VCA, right? Next, 2 pi is like again here. It is 0, na? 2 pi is like a 0 here, right? So here you can check after VCA. After VCA means come at the starting point. Okay. You can check till this instant only VCA was maximum. After that, the dotted green is maximum. Dotted green is nothing but VCB. Okay. So if VCB is maximum, means what? Definitely your which diode will be in a conduction mode now? Diode D6 should turn on, right? Diode D6 should turn on because VCB is maximum. Current should flow from VCA, T5, load D6 and VB. So therefore D6 will turn on. So once D6 turns on, then the output voltage will be getting, it is equal to VCA. Okay. So till T1 is fired, we'll be getting output as a, yes, means till this instant, we'll be getting output is like this only. Okay. That is a VCB. So let me indicate here VCB. So this will be like this, right? So from here it will start, it will be reaching peak until this instant. This pulse is your VCB. Are you getting the point? So in the output, we are getting these type of pulses. These type of pulses. Please be careful. Here we are having a semi-converter. Here we are having a semi-converter. Okay. So the thing is, it is like a inductor is storing the energy, and after that, the next diode or the next diode and thyristor pair conducting now. Through that, inductor is releasing the energy actually. Okay, inductor is releasing the energy, right? Because here our voltage is not going into the negative values now, right? So next. Now here you can check, we're having the pulse like VAB plus VAC. Same, whatever the pulse width here, now from here to here, the same pulse width will be there from this point to this point. We'll be getting the same pulse width from this point to again this point. Okay. So it is like we're having the 3 pulses actually. 1, 2, and the third pulse here part and remaining part is here. Okay. So this is for alpha less than 60 degree. Let us discuss if alpha is greater than 60 degree, what will happen? If alpha is greater than 60 degree, what will happen? Okay, so let me indicate alpha greater than 60 degree. This is the Vs, right? This is the omega t. So 0, this is a pi by 3, 2 pi by 3, pi, 4 pi by 3, 5 pi by 3, and 2 pi, right? And 2. So we're having the voltages like a VAB, VBC, and again VCA, right? So this voltage is like a VAB, this one is a VAC, and this is a VCB, right? We know the alpha equal to 0 degree for thyristor T1 is pi by 3. Alpha 0 for thyristor T3 is a pi. Alpha 0 for thyristor T5 is a 5 pi by 3, right? Okay, so we're having alpha 0 interval instants. Next, now let us discuss for alpha greater than 60 degree, what will happen? Alpha greater than 60 degree. So V0, right? So pi by 3, 2 pi by 3, pi, 4 pi by 3, 5 pi by 3, 2 pi. Okay. Alpha greater than 60 degrees. So consider alpha equal to 90 degree. Alpha equal to 90 degree. So you can check here. For alpha equal to 90 degree means we need to apply the get pulse to thyristor T1 at this instant. Na? This is T1. Get pulse to thyristor T1. So this angle is like your alpha. This is your T1. Similarly, we need to apply the get pulse to thyristor T3 at this instant, T3, and we're going to apply the gate pulse to thyristor T5. Yes, it is 5 pi by 3. Yes, 60 degree, and here at this instant we'll to apply the gate pulse. So here, and this is here your T1, right? T1, T3, and T5, right? So now suppose at this instant we are triggering T1. At this instant we are triggering T1. Okay, so let us discuss what will happen. Okay, once T1 is triggered, so you can check corresponding to this point. Okay, corresponding to this point, yes, we are having the peak value is a VAC. Actually, we are having the peak value is a VAC, right? So, or before that, okay, before T1, you can check here T5 was in a conduction mode. Before T1, the T5 was in a conduction mode. So you can check the pulses whatever we are having. Okay, so before T1, it was a pulse like a VCB. It was a pulse like a VCB. So you can check the VCB pulse here. VCB pulse here you can check till 2 pi by 3 it is positive. Till 2 pi by 3 it is positive. Yes or no, right? And after 2 pi by 3 it is a negative, na? So during this interval, now you can check the circuitry. In this circuit we are having a freewheeling diode. Okay, so when VCB is negative, na, it is like our inductor will be releasing the energy through the freewheeling diode. Okay, inductor will be releasing the energy through the freewheeling diode. Means instead of releasing the energy through your thyristor T5 and that respective diode, inductor will release the energy through the freewheeling diode. Okay, because the lesser opposition. So we'll be getting the pulse like this. Okay, VCB will be there. From which instant you can check VCB will be here from T5 till this instant, that is a 2 pi by 3. Okay, so I'm writing here this type of pulse will be getting. This is your VCB. From this to this point, it is a 0. Next, T1 is triggered. Okay, so you can check when T1 is triggered, it is like your VAC is a peak. VAC is a peak value. Okay, so when T1 is triggered, yes, you can check when T1 is triggered, definitely your T5 will turn off. Okay, so along with the T1, which diode will conduct? Along with the T1, yes, you can check the diode that should be in a conduction mode. That will be decided by the voltage VAC. Right? So voltage VAC means VA T1 load D2, and again back to the VC means D2 will conduct. That is the D2 will conduct. Right? So when T1 D2 conducts, in the output will be getting the VAC waveform. So you can check the VAC waveform will be getting. So this type of waveform will be getting in the output, right? Next, you can check here where triggering the thyristor T3 at this instant. Okay, so you can check from here to here. VAC is a peak value. After that, we're having a VBC, na? But you can check in order to get the VBC in the output, thyristor T3 should be fired, na? But where we're firing the thyristor T3, we're firing the thyristor T3 at this instant. Okay, so the point is from this point to this point. Okay, only our thyristor T1 and the respective diode in the sense your T1 and D2 only will conduct. Okay, T1 and D2 only will conduct, because here VBC will not appear in the output voltage till we apply the gate signal to T3, right? Unless and until your T3 is turned on, you will not get the VBC in the output, na? Right? So that's why here in the output will be getting only, yes, which pulse? That is the VAC pulse, and you can check till 4 pi by 3 only. We're having a VAC pulse, that is a non-zero. After 4 pi by 3, VAC is a 0. That is a negative. So our inductor will release the energy. So that's why it is releasing the energy, right? After that, what will happen? You can check at this instant we are triggering the T3. We are firing the T3. Okay. Once T3 is fired, so corresponding to this point, you can check VAB is at its peak value, na? VAB. This is your, yes, VCB. After that, we have drawn VAC, right? Next, we'll be having the VAB. Now you can check T3 is fired. T3 is fired here. Okay, so we are firing the T3. Once T3 is fired, T1 will turn off. Okay, T1 will turn off. Okay, so here, in order to get the VAB in the output, yes, which diode will be in a conduction mode? T3 and D4 will be in a conduction mode. So T3 and D4 will be in a conduction mode. So here it is a 0. Okay, so that's why we'll be getting the in the output we'll be getting the VB and A. VBA. So it is a just a minute, this is VAB, na? This should be the VBA. This should be the VBA, right? So we'll be getting this type of pulse, and this will be continuing till, yes, only till 2 pi, only till 2 pi, because after that it is a negative, na? Right? So that's why we'll be having the 0 here, and like this pulse will be getting. So VCB, VAC, and VBA pulse will be getting. So for alpha greater than 60 degree, actually the thing is we are having the zero interval present. We are having a zero interval present because freewheeling diode is in a conduction mode, right? So here we'll be having the freewheeling diode in a conduction mode. Let me write here freewheeling diode. This is also the freewheeling diode. This is also the freewheeling diode, right? Freewheeling diode, right? Now, yes, can we identify this point? Yes, what is this point? This point is like it is pi by 3 here. Pi by 3 and plus alpha. So this point is pi by 3 plus alpha. And what this point indicates, this point is like 4 pi by 3. 4 pi by 3. Okay. Similarly, we need to now derive the expressions. We need to derive the expressions for alpha less than 60 degree, alpha greater than 60 degree. Okay. So for alpha less than 60 degree, so in order to derive the expression, yes, we need to find this point. It is like this instant is like your alpha, na? We consider it is a 30 degree, and this point is like pi by 3. So pi by 3 plus alpha till this instant 2 pi by 3, and from 2 pi by 3 till this instant, and this instant is like your, this is a pi, so this is your alpha, pi plus alpha. Okay, so let us derive the expressions for alpha less than 60 degree and next alpha greater than 60 degree. So let me write here. Yes, for alpha less than 60 degree, for alpha less than 60 degree. Yes, what is the V0 average? You can check the waveform for V0 average. Okay, so it is like a 3 by 2 pi. I am writing 3 by 2 pi because we are having 3 pulses, right? This is the one pulse only. VAB and VAC, this is the one pulse only. Okay, so let me write it as a 3 by 2 pi. It is a 3 by 2 pi, right? Into, I am writing it as an integration from this point to this point. Okay, this point to this point only. We are having VAB, na? So it is like a pi by 3 plus alpha till this instant, that is a 2 pi by 3. Pi by 3 plus alpha till 2 pi by 3. During this interval, what is the voltage? It is a VAB, na? VAB. VAB is VML into sine of omega t. VML into sine of omega t into d omega t. This is the one thing. Plus next we are having, you can check this, we have considered, na, this pulse VAB. After that we are having the VAC also, na? VAC is from 2 pi by 3 till pi plus alpha, na? This is alpha, na? This is pi plus alpha, so this is pi plus alpha. Okay, so it is 2 pi by 3 plus 2 pi by integration from 2 pi by 3 till pi plus alpha. Okay, 2 pi by 3 till pi plus alpha, right? Pi plus alpha. So now here, yes, what is the waveform we are having? It is a VAC. So for VAC, can we write the expression? Yes, VAC. You can check. This is a VAB we are having. Okay, VAB we have written. It is a VML into sine of omega t, na? This is a VML. So how to write the VAC waveform? You can check. VAC is lagging to VAB by angle 60 degree, na? Pi by 3 radian. So VAC is equal to VML into sine of omega t minus pi by 3, na? Omega t minus pi by 3, right? So we are having VAC. So let me write VML into sine of omega t minus pi by 3 into d omega t, right? So we need to simplify it. So it is equal to 3 into VML divided by 2 pi into integration of sine of omega t. Integration of sine of omega t is a minus cos of omega t, right? Limit pi by 3 plus alpha to 2 pi by 3, right? Plus integration of sine of omega t minus pi by 3, that is a minus cos of omega t minus pi by 3, na? And limit 2 pi by 3 till pi plus alpha. This is the one thing, right? So we can write it as is equal to 3 VML divided by 2 pi into minus cos of 2 pi by 3 plus cos of pi by 3 plus alpha, right? Minus cos of, yes, pi plus alpha minus pi by 3. So it is a pi minus pi by 3, that is a 2 pi by 3 plus alpha. And next thing is a plus cos of, yes, 2 pi by 3 minus pi by 3, that is a pi by 3. Yes or no? Right? So further we can put the values here. Yes, therefore V0 average is equal to, I can write it as 3 VML by 2 pi into, yes, it is a, you can check cos pi by 3 minus cos of 2 pi by 3. Okay, so cos, that will be 1 plus, okay, and this can be written as cos of pi by 3 plus alpha next we are having a minus cos of 2 pi by 3 plus alpha. So cos of 2 pi by 3 plus alpha can be written as pi minus pi by 3 minus alpha, na? Right? So further we can write it as is equal to 3 VML divided by 2 pi into 1 plus cos of pi by 3 plus alpha minus, yes, cos of 180 minus theta, it is a minus cos theta. So plus cos of pi by 3 minus alpha, right? So which is equal to 3 VML divided by 2 pi into 1 plus, you can write cos A plus B plus cos A minus B. So 2 times cos of pi by 3 into cos of alpha, na? So which is equal to 3 VML divided by 2 pi into 1 plus 2 into cos pi by 3. So it is a 1, na, into cos alpha. This is the expression for your V0 average. V0 average. Is this clear? Right? V0 average. This is for 3-phase semi-converter. Next, can we write the V0 RMS? V0 RMS is equal to, same we need to put here 3 by 2 pi integration from pi by 3 plus alpha to 2 pi by 3. Okay. So 3 VML divided by 2 pi. I need to put this 3 by 2 pi, right? 3 by 2 pi into, I can write integration from pi by 3 plus alpha to 2 pi by 3, no? Yes, it is a 2 pi by 3 VML square into sine square of omega t into d omega t, right? Plus second thing is integration from 2 pi by 3 plus alpha, sorry, 2 pi by 3 till pi plus alpha, no? And what thing we are having? We are having VML square into sine square of, yes, VML square into sine square of, let me write it as a omega t minus pi by 3, right? Omega t minus pi by 3, right? So to the power 1 by 2. Okay. Will you simplify this? Okay. So simple thing, we need to replace sine square of omega t with 1 minus cos of 2 omega t divided by 2, right? Okay. So this is a V0 RMS. Next, for alpha greater than 60 degree, for alpha greater than 60 degree, yes, we can write V0 average is equal to, you can check the waveform. Yes, this one is, we are having 3 pulses, na? So it is 3 by 2 pi. 3 by 2 pi. You can write integration from, yes, here we are having a VAC, VBA and VCB. Okay, anyone interval you can use. Okay, So you can check it. This interval is like pi by 3 plus alpha, this point till this instant. Now this instant is 4 pi by 3. So pi by 3 plus alpha till 4 pi by 3. Right? Pi by 3 plus alpha till 4 pi by 3. Yes, what is the waveform we're having? It is a VAC na? And VAC waveform, yes, VAC waveform we have written the expression. Just a minute. Here it is we have written VML into sine of omega t minus pi by 3. Okay. So VML into sine of omega t minus pi by 3. Into d omega t, right? So it is equal to 3 VML divided by 2 pi into this integration of sign is minus cos of omega t minus pi by 3. Okay. Limit pi by 3 plus alpha till 4 pi by 3. So if we check, it is 3 VML divided by 2 pi into which we can write it as a cos of pi by 3 plus alpha minus cos of, just a minute, pi by 3 plus alpha minus pi by 3. So that will be plus minus pi by 3 will get cancelled out now. Only thing is cos alpha will remain. Next, cos alpha minus cos of 4 pi by 3 minus pi by 3, that is a pi. 3 pi by 3, yes, that is a pi. So we can write it as which is equal to, therefore V0 average. So therefore V0 average is equal to, it is like 1 plus cos alpha, 3 VML by 2 pi, 3 VML divided by 2 pi into 1 plus cos alpha, right? This is your V0 average, right? What you mean to say, Rajit Tyagi? Yes, please. Hello. Rajit, you can unmute and speak.
Hello, sir.
Yes.
Sir, go to the slide number 111.
Yes.
111, sir, slide number.
111.
Yes. Sir, here we are taking just the first part from first two parts. No, sir. Go to the waveform of this one, alpha less than 60 degree.
Okay.
Sir, here we are taking. Oh, okay, sir. Okay, sir. I made mistake something.
Okay.
Yeah, yes, sir. Got it, got it.
Okay. Yes. Yes. Right. So this is the V0 average. Similarly, we can write V0 RMS is equal to 3 by 2 pi integration from, oh yes, pi by 3 plus alpha to 4 pi by 3. It is a VML square into sine square of, we're having a omega t minus pi by 3. Into d omega t to the power 1 by 2, right? Okay. So no need to simplify here, right? So this is about the three-phase semi-converter, right? Three-phase semi-converter. So here a point to be noted: if alpha is greater than 60 degree, na, then your freewheeling diode will be in a conduction mode. But if alpha is less than 60 degree, freewheeling diode will not be there in a conduction mode. Okay. Next, I will add some points regarding the effect of source inductance in a three-phase full wave rectifier. Okay, I will give the direct expression here, and after that we'll stop for today. Okay, so before that, three-phase semi-converter. input power factor expression. Input power factor. Okay. Same thing, we need to draw the waveform of that thing, that is IS, and after that we can simplify, okay, by with the help of Fourier series. Okay, but I am giving the direct expression here. It is under root 6 upon pi into pi minus alpha into cos square of alpha by 2. Right? If you want, I can add the derivation in the class notes. Okay, right? Okay. So this is the input power factor. Next thing is effect of source inductance. Effect of source inductance in 3-phase 6-pulse converter. So it is like we are having, suppose the 3-phase 6-pulse converter. This is a LS, right? So A, B, and C, and this is a LS we're having. Okay, LS, T1, T3, T5, T4, T6, and T2. Okay. RL, this is a V0, right? And the I0. Right? Effect of source inductance is observed, just like your single phase fully controlled rectifier we discussed them. Okay, so same in a 3-phase also the effect will be observed. Yes, you can check. Due to this LS, whatever the current here, na, that is the IA, that will not change suddenly. Yes or no? Right? And your IA is having a relation with your T1 as well as T4, no? IT1 and IT4. Similarly, your IB also will not change suddenly, and IC also will not change suddenly. Okay, now important thing, this should not be like this. Okay, this should be like this. Okay, so now you can check IA is having a relation with the IT1 and IT4 now. Similarly, IB is having a relation with your IT3 and IT6 also. And IC is having a relation with IT5 as well as your IT2. Okay, means due to the source inductance, definitely your IA, IB, IC will be getting affected, and at the same time your IT1, IT2, IT3, IT4, IT5, IT6, all these thyristor currents will be also getting affected. So effect will be same as that of your whatever we discussed. Okay, in that case, single phase rectifier. In the single phase rectifier, what we observed, due to the source inductance, the average overall average V0 average value of the output voltage is it decreases, na, right? So same thing is happening here. I'm giving the expression directly here. V0 average is equal to 3 VML divided by pi into cos alpha minus 3 into omega into LS into I0. Okay, divided by pi. 3 omega LS into I0 by pi, right? 3 VML divided by pi into cos alpha means what? It is the output voltage without LS. Output voltage without LS. Okay, and this is like your drop in a voltage due to LS. Drop in a voltage due to LS, right? So let me write here. This indicates output voltage without LS, and this is like a drop in voltage due to LS. due to ls, right? So far they have not asked the questions, right? So please go through the expression, right? Next, we can write the expression for cos of alpha plus mu, same as that of whatever we wrote in the single phase rectifier, na, right? Is equal to cos of alpha minus this drop. Okay, so it is like a 3 into omega into ls, but this drop is like your vms, right? These two expressions. Okay. So now only one point is remaining, that is the dual converter, and after that we will discuss the numerical. Hardly I think 4 to 5 numericals are pending, right? So tomorrow at the start we will discuss that, and after that we will start the DC to DC converter, right? Okay. Okay, I will stop here. If you are having any doubts, please ask.
Sir, that regarding that last one, sir, that working, just could you explain this last three-phase semi-converter, why VAB we are getting,
Why VAB?
like why VAB conducts only for some part and then remaining is followed by VCA? That part I lost my net, sir.
Here, na?
No, sir, previous one, alpha less than 60. This one, sir.
At this instant, okay. Okay. So at this instant, we are triggering thyristor T1.
Yes, sir.
So due to that, what will happen? The corresponding peak voltage is VAB, na?
Yes, sir.
So with the T1, which diode will be conduction mode, that will be decided by your voltage VAB. So with the T1, you can check D6 will conduct, yes or no?
Yes, sir.
Okay, so that's why output voltage will be like your VAB.
Okay, sir.
This will continue till this instant only. Why? Because after this instant, you can check VAB is lesser than that of VAC, na?
Yes, sir.
And VAC to the phase A, we are having T1 is connected.
Yeah.
T1 is already in the conduction mode.
Yes, sir.
So as VAC is a peak value, so which diode will be in a conduction mode? D2, na? So that's why when D2 conducts, your D6 will turn off.
Yes, sir.
Then the output will be getting VAC, right?
Okay, sir.
Okay.
Thank you, sir.
Okay. Yes, please.
Hello, sir.
Yes, please.
Sir, in the exam hall, there is you have to means, sir. Please tell us how to in a shortcut we have to draw the waveform and calculate it, because sometimes expression are very difficult to in semi-converter. We are getting a different type of waveforms.
Yes, yes.
Then for remembering expressions are very difficult actually, sir.
Very difficult. Yes.
Means is there any short trick or that is the only way?
Short trick means the very first thing is you need to memorize the circuit diagram.
Yes.
And
Means
after that,
steps,
that
means
circuit diagram
procedure.
operation. Hello.
Yes, sir.
Then from that you can understand the how is the nature of this waveform.
Yes.
If you check apart from the semiconductor, only semiconductor is having something different type of waveform, na? You can compare you can compare other converters. We're having somewhat more or less similar kind of things.
Okay.
If it is a REL load with freewheeling diode, then you will be getting a 1 plus cos alpha type thing. Okay. If only all the thyristors are present, then you will be getting it is a into cos alpha type thing, right? Tomorrow I will give you the overall summary of for which converter what is the expression, okay, and why it is only proportional to cos alpha, why it is proportional to 1 plus cos alpha, right?
Sir, another doubt is, sir, in the
Because we have a
previous
very
class,
large number of circuits and large number of loads also, right?
sir, actually, I am not following means that remembering way actually in every time.
Okay.
So in the power electronics, means the test series, I got some less marks, sir, always.
Okay. Mhm.
Sir, actually, means every time I'm remembering, but it is not remembered for the next 2 days. Every time for
Okay.
long time, so I have to need some short tricks actually.
Okay.
Or sir, and sir, in the previous one, in a question you write the KVA rating. That KVA rating
Okay.
is the average of that primary and
Yes.
secondary.
Yes.
Is it actually following the transformer rule? Sir, means for a transformer, the KVA rating of primary and secondary always be equal.
Equal, right? But the thing is here.
But you said, sir, in the power electronics it is different. How in power electronics it will be different?
No. Tomorrow we are going to discuss one more question. In that we will check the KVA rating we have calculated, just like your whatever we calculates na,
Yes.
primary and secondary both equal.
Okay.
In that way. But here two ways we are having, because the thing is in your machines or in your power system, our power transformers are generally fully loaded na, for all the time.
Yes.
And the current flowing through that secondary part or the primary part is always non-zero. But in power
Okay.
electronics, due to the switching, it is like either suppose in that numerically, if you recall, when the current was flowing in the upper part of the secondary winding, then the
Only for
secondary
pi angle.
lower part current was zero.
Zero. Okay.
So that's why like that they have calculated. But as long as power electronics is considered, you need to be ready with these two type of things, okay, for the transformer KVA rating.
Sir, in an ideal case, we are assuming that current is constant.
In ideal case means
That high inductive value.
load current is constant.
Constant.
Yes.
But in actual practice, is it feasible? Current is definitely somehow less. So
No.
it will
We
be
are
actually
getting the constant current. We are getting the constant current.
in CRO. Can we visible this type of waveform?
Yes.
That is
Whatever your
constant,
practical
I know.
rectifiers, whatever the practical rectifiers we are using na in real
Yes.
life, right? Those practical rectifiers are giving the constant voltage as output as well as constant current also. If the load is highly inductive, the current will be nearly constant.
Means if there is any induction or something.
No.
Induction
If
motor.
the current is constant or not, it depends on your load. But our rectifier is giving the constant voltage. That is what I'm saying.
Okay. Constant
Right?
voltage.
Because this type of output, whether can I apply to DC motor? Suppose this is V0 we are having na. Can I apply this to the DC motor? No, na.
No, sir.
So that's why actually we are adding at the output side, we are adding the filters to the rectifier. Okay.
Okay, means overall the system will be.
Yes,
Because
overall
but
voltage will
in
be
our
getting the constant.
but in our lab when I done a for that is a bridge converter, we also getting some variation, means exact that type of waveform is not getting always. After
No,
this
but
is
bridge
sir,
converter in
bridge,
power electronics lab, you are saying.
but after that means inside that heavy control system is there.
Okay.
Okay. After that also we are not getting, because some fluctuations are there because of the, I think that SCR or that power electronics
Fluctuations means
device.
you are saying constant voltage you are not getting, or
Means
actual voltage
that
waveform, whatever we are discussing, that you are not getting there in lab.
means that waveform we are drawn in the paper, that will be seen on the CRO. Means that will be fluctuating.
Yes.
Means not that following the sinusoidal waveform actually. Means some of the harmonics I think present also.
Okay. No, that might be due to other reasons also. Okay, that might be due to some of the passive components in your circuit maybe not functioning or etc. But in your machine laboratory also you might be having it na. Hello.
Okay, hello, sir.
Hello.
Hello.
In your DC machines laboratory also you might be having that rectifier unit.
That yes, but I just shown
High current and high voltage rating.
Okay.
Right? If possible, please try. But on CRO you cannot observe that waveform of that high current. Okay.
When I was in college,
Actually,
sir,
that is the actual rectifier. That is the
Okay.
actual rectifier which
Okay.
we are using in order to feed the DC motor. Right?
Okay.
For power electronics laboratory, you will be having this type of circuitry only. Means these are the basics now. At
Okay.
undergraduate level, we cannot. So undergraduate level is like a basic thing only, na.
Yes, sir.
And at this level, you are studying all the concepts, all the power system, machines, power electronics, control system. When you go for the PG, then you will be getting the advanced techniques, right?
Okay.
Okay. Right.
And sir, sometimes you please say about your preparation strategy in study. Actually.
Yeah, I will. Okay. But the thing is, we are actually lagging with the syllabus only, na. So that's why I am not.
Means for some 5 minutes for motivation
Yes,
only.
I will at the end. I will. Okay.
Okay. Thank you, sir. Thank you.
Yes, please.
Hello.
Yes, please.
Hello.
Yes.
Sir, last
You are
one.
audible. You are audible. Please.
Effect of source inductance, sir.
Effect of.
Sir, last one.
Last one. Okay. Yes.
Sir, circuit diagram.
Circuit diagram. Yes.
Sir, here T5 is SCR, no? Thyristor.
T5. Hello.
Hello.
Please.
Sir, T5 is thyristor or diode?
Okay. Thyristor. Thyristor only.
Sir, one problem.
Okay.
Sir, hello.
Yes, please.
Sir, freewheeling diode. What is the purpose of connecting freewheeling diode?
Where semi-converter.
Yes, sir.
Okay. Actually, to avoid that negative part, the thing is in the semi-converter single phase also we discussed.
Waveform negative, remove negative parts.
No, that is the one thing. And second part is in the that thing in a single phase semi-converter also we discussed now.
Yes,
Generally, semi-converter is having a inbuilt action of that freewheeling. Okay, through the 1 diode, but that causes the increase the current rating of the thyristor, right?
Okay.
So that's why we're keeping the freewheeling diode here.
Sir, it is also improve the power factor.
It is
Also improve the power factor.
Increase the power factor, that freewheeling diode.
Yes, sir.
Okay. I don't think so.
Sir.
Right.
Okay.
Okay. Because anyway, suppose if the freewheeling diode is not connected, then your inductor will be releasing the energy through 1 thyristor 1 diode also, na?
Yes, sir.
So output voltage will be same type of nature only.
Sir,
the thing is your low, yes, your source current, yes, in that case also source current will be 0. Here also source current will be 0, corresponding to the freewheeling action.
Okay.
Right. Okay.
Okay, sir. Thank you.
Hello, sir.
Yes.
Sir, you have derived the expression for B naught average in case of alpha less than 60 and greater than 60 in this semi-converter case, no, sir?
Okay.
Sir, we are getting the same expression, sir, but in case of freewheeling diode, some part of voltage is 0, no, sir. How we are getting the same expression, sir?
Okay. We're getting same expression.
Yes, sir.
2.21 plus cos alpha, and here okay. This is there, and please check once the calculations. There might be something. I will check this while uploading the class notes, right?
Yes, sir.
But as usual, this should be the different.
With freewheeling diode, we should get less, no, sir?
Yes, yes.
With freewheeling diode, average voltage should be less, no, sir, compared to without freewheeling.
No, but here it is not like a with freewheeling. We are having the different firing angles, na?
Yes, sir. But alpha less than 60, we are not considering the freewheeling diode action, no, sir.
Yes.
So there should be a difference, no, sir.
No, I will check once the calculations before uploading, right?
Yes, sir.
Right.
Sir, another one, sir. In case of single phase converter, we are analyzing like inductor is charging from alpha to, or in case of thyristor, alpha to theta and theta to some beta, it is go on discharging. In the three phase, there is no concept of theta, sir.
In a three-phase diode rectifier,
Yes, sir.
there is no concept of there is a concept of what you can say, the inductor is releasing the energy, but it is like if you check either a three-phase half-wave control rectifier or three-phase full-wave control rectifier. Okay.
Yes, sir.
Actually, during that respective interval, when your respective line voltage, if you consider that a three-phase full-wave rectifier, when that respective line voltage is greater than that of your VR, inductor was storing the energy.
Yes, sir.
And in that, after that, what is happening? Inductor is releasing the energy.
Yes, sir.
When respective devices will be in a conduction mode, and when the next pair of devices will be in the there, na, then inductor
Yes,
will
sir.
continue go on releasing energy through that pair also. So that's why
Yes,
it is
sir.
not going into the negative. You can check. Suppose let us consider ki we are having three single phase full wave diode rectifier.
Okay, sir.
Suppose we are having a single phase full wave diode rectifier, and suppose if the load is REL load, right? So which type of waveform will be getting? Whether we'll be getting the V0 negative here.
No, sir.
So same thing is here in the diode, right?
Yes, sir.
Right. In the diode rectifiers, actually we yes, generally the V0 will not go into the negative. But for half wave, single phase half wave, we have discussed na, it was having the beta na,
Yes, sir.
but it was like a single loop and single diode we had. But if you check three phase three pulse rectifier, in that case, when T1 was in a conduction mode, it is like inductor stores energy for some time interval. After that, it releases, and remaining energy inductor can release when T2 conducts.
Yes, sir.
Or that is D2, not T2, that is D2 in our case, right? Diode rectifier. And that
Sir,
will be
okay.
same thing, na? That is, it will be assisting only, right?
Yes, sir.
So that's
Sir.
why you will not get the negative pulse here, right? Okay.
Yes, sir. Sir, in all these cases of semi-converter and full control, we are taking the R load as a highly inductive load, so the load current is constant. Sir,
Yes.
why you have not taken like we have taken single phase that pulse, no, sir, from maximum to minimum and then maximum to minimum. That
Okay,
like,
okay. Generally, the thing is, in a single phase, actually the inductor is getting somewhat more time to release the energy.
yes, sir.
And in a single phase half wave we are having, you can check single phase half wave, it is like a one diode only we are having, one diode or one thyristor you can consider.
Okay, sir.
So inductor is having more time to release the energy. Means after pi or from theta to pi plus alpha, inductor is having
Sir.
that much of time to release the energy.
Yes, sir.
But whereas if you compare in a three-phase circuit, three-phase half wave control rectifier circuit, okay, we
Yes,
are
sir.
turning on thyristor T1.
Yes,
And
sir.
again, you can check what is the difference between, what is the angle difference between get pulse to thyristor T1 and get pulse to thyristor T2.
It
In a
will
single
be
phase
like,
half wave rectifier corresponding to 360 degree, we were turning on only one thyristor, that is a thyristor once only. But
yes,
in
sir.
a three-phase, if you recall, in a three-phase, the three-pulse rectifier, we are having a
Yes,
three
sir.
thyristors, and
Yes,
input
sir.
cycle duration is only 360 degree, na?
Yes, sir.
So in a 360, I am turning on three devices.
Yes, sir.
So that's why your inductor is getting a lesser time to release, na?
Yes,
And
sir.
it is getting the alternate path also. So that's why more your current for a three-phase, your current will be constant, right?
Yes, sir. Sir, what is the use of using semi-converter, sir? Is there any use of like getting voltages like more than the off control, or is there any harmonics increase, harmonics decrease in issue, sir?
No, actually the thing is, in a semi converter, you can check in a full converter we are having four controlled switches.
Yes, sir.
But whereas in a semi converter, you require a half controlled switches only. Means
Yes,
whatever
sir.
your full converter is doing the job, the same job is doing your half converter.
Yes, sir.
But that full, and in the case of RL load, the thing is, in a full converter, we require a freewheeling diode also to improve the voltage. But
Yes, sir.
whereas here, whether we require a freewheeling diode, no.
No, sir.
In a three-phase generally we are connecting, but in a single phase you can connect it or not, right?
Yes, sir.
So altogether your overall voltage, if you compare the RL load there in a fully controlled and RL load in a semi converter, you will be getting the improved V0 average.
In semi-converter, sir.
Yeah, in semi converter,
Okay, sir.
because negative pulse will not be there, na?
Yes, sir.
Whereas if
For
you
alpha
compare
greater
RL
than
load in
6.
full converter, if you compare RL load in full converter, you will be getting
Yes,
the
sir.
negative pulse, na?
Sir, that in that case, if alpha should be greater than 60 degrees, no, sir. To get a
Alpha?
negative pulse in full wave control, we should have alpha greater than 60 degrees, no, sir. In case of full converter, to get
In case
negative
of
voltage.
to get negative voltage, where you are saying in a
Full
three-phase.
wave, sir. Yes, sir. 3-phase, sir.
Okay. Yes. Then only
Okay,
then
sir.
that will be negative, right?
Yes, sir. Yes, sir. Then only there will be use of semi-converter. That voltage will be clipped to 0.
Yes.
Yes, sir. Thank you. Okay, sir. Thank you, sir.
Okay.
Good evening, sir.
Good evening.
Sir, in difference between half controlled and full controlled converter, single phase. Only in half controlled, 2 thyristors, 2 diodes are used. In full control, only total 4 thyristors are used. Is there only this difference or any other differences?
No, you can check the improved V0 average you will be getting in a semi converter.
Okay. And another
Semi
doubt.
converter means half converter.
Yes, sir. Another doubt, sir. If why we are not considering capacitive load, sir? Always RL, R and RL, RLE.
Okay. No. The thing is whether in real life we're having a capacitive loads.
Sir, in fax devices, we are using capacitor switching, that we are using power electronic converters, we are using.
No, but that capacitor you are not using as a load na in fact devices.
We are switching
In
devices.
fact, you are using the capacitors in order to help your power system.
Okay. In switching
Right? So
cable,
most of our loads are, you can check. R load we are considering because we are having a heater load. Na? Generally, you can think which type of loads are generally connected to the rectifier circuitry. We can connect DC motor, we can connect heater load, we can connect battery charging circuits. Yes or no?
okay. Sir, in
So
super
that's why
capacitor,
capacitive loads are not connected, right? If I am having capacitive load, na, then I will prefer the AC supply na, to it.
okay.
Yes, why to connect that DC supply, right?
And another doubt,
But
sir.
we are considering that RL load and those things because in drives we require, na.
If we connect
Because
RC
DC
load,
motor,
what is the
DC motor is your
response?
RLE load, na.
Sir?
DC motor is your RLE load,
Yes, sir.
right?
Okay, sir. Another doubt, sir.
Huh.
In freewheeling diode is replaced with normal diode. The normal diode also same function as freewheeling diode.
Yes, normal diode also can function the same way, right?
Okay, sir. In ESC prelims, the how many marks get from power electronics, sir? Means how many marks come from power electronics?
For
Prelims.
ESC prelims altogether, you are saying
Yes, sir.
prelims weightage, I think is around for mains it is very high weightage.
So prelims.
For prelims, I think on the first day only I gave, na.
I got a first day I'm absent, sir. I'm not watching this first video.
Okay. Exact weightage I will tell you. Okay. For GATE, I know it is roughly 10 to 12 marks for GATE examination. For your PSC is also it is a roughly 10 to 12 marks. Okay. And for
Okay.
ESC conventional, okay, ESC conventional it is around 75 to 85 marks. Okay.
Okay, sir.
Right. Prelims exact that number I will tell you. Okay.
Okay, sir. Thank you.
Right. Right.
Hello, sir.
Yes, please.
Am I audible, sir?
Yes, please.
Sir, I have a normal doubt. Sir, these we have different types of converters and we got different types of formulas for each one.
Okay.
How are we supposed to remember all these at the time of the gate for a given question?
Okay. Please keep it in mind as long as your GATE or ESC examinations are considered. Okay. Definitely those will not be based on your formulas, right? If you understand the concept, right?
Yeah, sir.
Okay, so at the time of examination, you can recall it, right? So
Okay,
simple
sir.
thing, as long as your three-phase circuits are considered. Okay, for three-phase circuits, my suggestion is please try to memorize these expressions. Average value, RMS is not required at the time of examination. So you can in a short, okay, you can solve it. Okay.
Okay.
But average, what is the difference in a single phase V0 average, three-phase V0 average? Okay, that simple techniques, right? You can develop, okay, and you can memorize those expressions. We know it is a if RL load with freewheeling diode is there, then your V0 average is like a proportional to 1 plus cos alpha. If the freewheeling diode is not there for a continuous conduction, then V0 average is proportional to cos alpha, right? Like these things, like these small tricks, okay, we need to develop.
Okay.
Right.
Sir, and another one, sir. In the morning class, I got like the host is in another meeting. After recently, I saw there are 2 videos about that. One is 2.5 hours,
Okay.
and
Okay.
if anything happens again, we have to wait till how much time, sir?
If anything happen, okay. No, in the morning class, actually the thing is whatever the link they give to you, that was
Yes,
for due to the overlap in the link, right? But always keep it in mind, if by any means or by if any issue, if the class is interrupted, please wait for 10 to 15 minutes, right?
Okay, sir.
And they have, I think they gave the new link within the 15 minutes.
Actually, it took some time, sir. More than 15 minutes, I think.
Okay. Generally, these type of problems will not occur. Okay.
Okay, sir.
Right. That was very rare, means due to the link overlap actually. For the same link, the another faculty was started that class at 7 and that's why correct at 7 a.m. our class got interrupted, right?
Okay, yes, sir.
Yes.
That's it, sir.
Yes.
Hello, sir.
Yes, please.
Good evening, sir.
Good evening.
Sir, just I'm not a doubt, sir, but just sir, how we can memorize this so many for electronic formulas?
Everybody is having the same problem. Everybody is thinking about the same.
Confusing, sir.
Sir, how to memorize this? Okay. Now the
R
thing
load,
is,
full wave off.
yes,
Can you
I
explain?
know. Compared to that of your other subjects, this subject is somewhat vast actually, right?
Yes,
and
sir.
most of the mathematical part is there, and it is a combination of your electronics and other our missed devices. That is the network combination, right? We can say, or other subjects also, EME and those subjects also, right?
Sir,
But please try to, very first thing is you need to do is try to practice the circuit diagrams. Unless and until you memorize the circuit diagram, you cannot proceed at all, right? If they ask the question like a single phase full wave controlled rectifier, so very first thing that should be okay in your mind. If you read that question, okay, we are having got 2 types of the single phase to full wave controlled rectifiers, right? One is a bridge type and second one is a center tapped transformer, right?
Yes.
So like this, if you memorize those, then you will be directly clicking that circuitry. Okay, once you understand the circuit, memorize the circuit, you can easily recall the operation, and from the operation you can while the examination also in the rough you can draw the waveform, right? That is the only thing, because the short things or the mugging of the concepts, that will not work here at all. Please believe me. In your exam, in your university examination, that may work, okay?
Sorry,
But
sir.
here your mugging concepts will not work at all. And here you can think during your examination in the GATE or ESE, you are having, you need to, there will be questions, right? From all the 10 subjects, na?
Yes,
And
sir.
all these 10 subjects means your engineering, I think around 20 subjects will come there, okay?
Yes, sir.
So memorizing memorizing, I cannot say, but mugging the concept will not work here. So as long as polytron is considered, please try to draw that circuit diagram, right?
Okay, sir.
And we're having the circuit diagrams in this chapter also, whereas in the next chapter also, and the inverter also, right? But fortunately, we are having a somewhat lesser contents in a DC to DC converter and your inverter, okay? Because in an inverter we are having only single phase half bridge and a 3-phase bridge type circuitries, okay? But whereas if you recall, if you consider this rectifier, this is a very big chapter, okay?
Yes.
Try to practice, try to draw the circuit diagrams, okay? Try to simplify these expressions, okay?
Sir, sir.
It is very interesting. Everything,
Which areas
mathematics
we will
here,
more
okay?
concentrate on that, sir?
Yes.
Which area we will more concentrate on that, sir?
Okay. I mean, as long as polytron is considered, I cannot say ki, on a particular topic on which area you should concentrate, but I can say first chapter, second chapter, that is the rectifier, third chapter, and the fourth chapter, inverter. These 4 chapters are very important. Comparatively, AC to AC converter is having a very less weightage, okay? But your DC to DC converter and inverter questions are comparatively easy, okay, than that of this rectifier, right? In an inverter also we need to use that Fourier series analysis, okay? That's why here I have covered in detail, so that there we can directly use the whatever results, okay? Please try practicing the circuit diagrams, okay?
Sir, if it is possible, can you give the short form for this chapter, sir?
Short form for the chapters.
Rectifiers only, sir. Rough wave.
Okay. No. Tomorrow what I will do, tomorrow when we finish the chapter, after that I will give you the circuitry, which type of circuitry is there and what is the expressions, right?
Okay, sir.
And accordingly you will understand, because when I put all the circuitries on one page, then you will understand that for this type of circuitry, how the V0 is proportional to which thing, right?
Yes, sir.
And you will be getting an idea. There is a relation between single phase and the 3-phase also. As long as your LAC is considered in your source inductance, there is some similarity in the single phase expression as well as in the 3-phase expression also, right? That I will tell you tomorrow, right? At the end of the chapter.
Thank you, sir.
Hello, sir.
Yes, please.
Sir, in a 3-phase of full wave diode rectifier, sir.
Okay. 3-phase full wave diode rectifier.
Yes.
Yes, here it is. Full wave.
Circuit diagram. Yes, sir.
Full wave. Okay. R load, RL load.
Sir, RL load.
Okay.
Sir, in a full wave control rectifier, sir, we have used the thyristors and the control signal for thyristor when to turn it on after means any interval alpha. But sir, in diode rectifier, which diode operate and when we will decide it, sir? Actually.
No. Actually, the thing is which diode will operate, which diode will conduct, that will be decided by your line voltage.
Yes.
If you check here line voltage, we are having 6 line voltages,
Yes, sir.
So So you can check from 0 to pi by 3 VCB maximum na.
Yes, sir.
You can compare during this interval VCB maximum and remaining 5 voltages are at a lesser voltage. Remaining 5 line voltages are lesser. Okay.
Yes.
So you can check VCB maximum means what? Here you can check VCB maximum is current should flow from VC to VB.
Yes, sir.
So how the current will flow from VC to VB? So that here, yes, it is like VC D5 na.
Yes, sir.
Next load D6 and again VB means which two diodes will be in a conduction mode D5 and D6.
Yes, sir.
Right? Like this means that respective line voltage will decide which diode should conduct.
Sir,
right?
but the waveform we have taken that are depend on the circuit operation, sir. Actually, how circuit operates.
No. This is the supply waveform. This is the supply waveform.
Okay.
Your output voltage depends on the circuit operation.
Okay. Okay. Sir.
When you apply the three-phase supply here, na, right, at this side ABC.
Yes, sir.
This supply voltage waveform is nothing but this one, right?
Yes, sir.
Okay.
Okay, sir. Thank you.
Okay.
Hello, sir.
Yes, please.
Sir, in three-phase full wave control rectifier.
Three-phase full wave
Control rectifier.
Okay. Three-phase full wave controlled rectifier. Huh.
Sir, in this alpha greater than 60 case.
Greater than 60, na?
Sir.
Yes.
Sir, in this waveform, not this, sir, alpha less than 60, I think, sir.
Less than 60. Yes. Sorry, this is greater than 60.
This one, sir, this one.
This one?
This one.
Sir,
in this I not get that output voltage becoming 0. That part, could you explain once again?
Okay. Please listen. At this instant, thyristor T1 is triggered.
Yes, sir.
Before that, T6 was in a conduction mode.
Sir.
So you can check when T1 is in a conduction mode. So with T1, your T6 will start conducting and your output voltage will be VAB, na? Same as that of this one. Na? Peak value, which one is there? VAB.
Yes, sir.
So therefore your, not peak value, with T1, T6 will conduct. So therefore VAB, and this VAB will be 0 at pi. After that VAB is negative, na?
Sir.
So you can check in this circuit if VAB is negative, right? So
yes,
whether our R load is there and which two thyristors were in a conduction mode, it is like a T6 and T1, na?
Yes, sir.
So when VAB goes negative, what will happen? Whether our thyristors will allow the reverse current. VAB negative, the meaning is VAB. It is VAB is a negative, na?
Yes, sir.
The meaning is current should flow from B to A, na?
Sir.
So whether our thyristors T1 and T6 will allow the current from B to A. It is a reverse current actually. So you can check in a resistive load, yes, whether the reverse will current circulate, no, right? So that's why during that interval it will be 0.
Okay, sir.
Right? So that's why I'm getting
Okay,
only
so
this part. But if you check for RL load, it is a continuous conduction, na?
Sir.
So that's why we'll be getting the negative. Why the continuous conduction was there? Because inductor was releasing the energy, na?
Sir.
Right? So when inductor releases energy, so inductor was releasing the energy in opposition to that of whatever the supply voltage is there, right?
Yes, sir.
Means even though your VAB is negative, inductor will release that energy in opposition to that of the supply voltage. That's why the respective thyristor will be in a conduction mode.
Okay.
But here it is inductor is not present. So whether the another energy is present here to make our thyristor, that is the T6 T1 into the conduction mode, no, right? Only resistor is there. So that's why that is, right?
Okay, sir. Sir, and one more doubt, like in this, in the alpha less than 60 case, we took that because it is reverse biased, current cannot flow. So could you take that alpha less than 60?
Here it is, na?
Sir.
In
Sir,
that,
so in this, when it is becoming that, when the diode is becoming, sorry, the thyristor is becoming reverse bias, that's why like we have taken that case, sir. So usually thyristor will switch off when the current through it becomes 0, and then as second case we want the reverse voltage to appear across it, na sir.
okay,
Sir, but in this case, will the current like become 0 first and then the reverse voltage come like that? Something will be there here, sir.
Means you are saying from here to here when T1 conducts, at this instant how the T1 is turning off, right?
Sir.
Okay. The thing is, when T3 turns on, na?
Sir.
When T3 turns on, you can check this circuit. When T3 turns on, automatically the reverse voltage will be appearing across it. Na? We are having the two commutation circuits we discussed. One is a voltage commutation, second one is a current commutation. So voltage commutation means what? It is like a reverse voltage was appearing, and due to that thyristor was turning off.
Yes, sir.
Definitely current was becoming 0, but that was due to the reverse voltage. Na? Now you can check here, when T3 conducts, here it is VB, here it is VB, here it is VB. So voltage across thyristor T1 is VBA, na? Sorry, VB, that is VA minus VB, that is a VAB. So if your VAB is negative, whether our thyristor T1 will conduct?
No.
So that's why it is turning off.
Sir, so the current will become 0
Current will
because
become
that reverse
0.
voltage.
Current will also become 0 due to that reverse voltage.
Okay.
Right?
Sir, and in the last one, sir, three-phase semi-converter circuit also, in the waveform, like that 0 in the voltage, that I not get, sir.
Where, just a minute. Here. This one? Hello?
Sir.
Okay. In that, how this 0? Okay.
Yes, sir.
Okay, you can check. Here I am firing T1, na?
Sir.
So which voltage will appear? You can check corresponding to this instant here. VAC is maximum.
Yes, sir.
And to the terminal A, our T1 is connected.
Sir.
So you can check to the terminal A in this circuit. T1 is connected. VAC is maximum, and this side, second side, we are having the lower side, we are having only uncontrolled switches, na?
Yes, sir.
We can control the upper switches by controlling the gate signal, but these lower switches, these are uncontrolled switches.
Yes, sir.
So whether out of these three, which diode will be in a conduction mode, that will be decided by that respective voltage. So now you can check when the gate pulse is applied to thyristor T1 here, that is VAC is a maximum.
Yes,
so when VAC is maximum is as soon as your thyristor T1 turns on, right? As VAC is maximum, so automatically your diode D2 will turn on. Because compared to the remaining two diodes, the maximum forward voltage is appearing across diode D2 because VAC is maximum, na?
Sir.
So that's why T1 and D2 will conduct.
Okay, sir.
Right? And next you can check after T1, D2 what we are having. Suppose till this instant we are having VAC, na? After that it is a VBC maximum, na?
Sir.
But in order to get the VBC in the output, which thyristor is required? VBC. To the B we are having T3 connected. But whether we applied the gate pulse to T3 yet, we are applying the gate pulse to T3 here, na?
Sir.
So whether VBC will appear after this point here in the output? No. Unless and until you turn on the T3, your VBC will not appear in the output, na? So that's why our VAC will continue till this instant.
Okay, sir.
Right?
Okay. Sir, in this circuit, there is no use of freewheeling diode for alpha less than 60, sir. Even if it is not there, does it make a difference?
Not required. Because just like whatever we discussed in the diode rectifier case, na? Same thing is happening here. Means inductor is storing the energy and also it is releasing the energy.
Yes, sir.
And through that respective source and your respective thyristors.
Sir.
Right?
Yes. Okay, sir. Thank you, sir.
Hello, sir.
Yes, please.
Sir, can we say that as we increase alpha, the ripple in the output voltage decreases?
As we increase the alpha,
Ripple content, ripple factor in output voltage will decrease. I mean, we get DC wave.
Okay. No, in which case you are saying, or in general? In general,
sir. Any case, control, uncontrolled.
You can check the ripple factor. It is RMS form factor is equal to your RMS divided by average, na?
Yes, sir.
Please check when if alpha increases, whether your RMS value increase or decrease.
RMS.
Alpha increase means your area decreases, na?
Yes, sir.
So RMS value will decrease.
Decrease.
So your form factor will decrease.
Okay.
Right. So that's why your ripple factor, you can say form factor decrease means ripple also will decrease.
Okay. So so that we get straight DC wave, no?
No, we cannot say like that. I'm saying in the case of ripple factor, whether you are saying for ripple factor or ripple.
Ripple. I mean,
ripple means there are two meanings. Ripple, there are two meanings. The difference between maximum value and minimum value, that is also known as a ripple. The another is whatever the pulses we are getting, na? Those are also saying that it is a pulse or the ripples also.
Okay.
Right.
Okay. And sir, why don't we consider RLE load for three-phase converter?
Why RLE load?
Yes, sir.
Same RL load with a constant current, that is a highly inductive, and RLE load with highly inductive, both are same.
Okay.
Because
so
in both the cases we are having I0 constant, na?
Yes, sir.
Right. So only thing is, while finding the I0 average, right, we need to consider V0 average minus E by R in the RLE load. But here directly we can write. Okay. That I will summarize all these things, na, tomorrow at the end. Okay.
Yes, sir. Yes. And sir, one more that.
Yes. And every batch I am getting same type of thing. When when we will be nearly at the ending of the chapter, na, every batch students are asking same issue. Sir, how to memorize, how to prepare and those things. Okay. So generally I put that one page summary type thing in front of them. Okay. So that when they see all these formulas and all these concepts on one page, then after that they will think that somehow this is somewhat having similarity and those things. Okay.
Of course, sir. Yes, sir. And sir, can we connect induction motor to three-phase converter and
induction motor to
three-phase converter? Can we control the speed of that induction motor?
No. We are using the inverter actually.
Okay. You mean
because
DC
induction motor
AC.
basically requires three-phase supply, na?
Three-phase supply, yes.
And here we are dealing with a rectifier, that is the DC output.
Yes.
Right.
Okay. Yes, sir. And sir, what is can you distinguish between continuous case and discontinuous case? And I didn't get that.
Continuous.
Point. When to use continuous and when to use discontinuous?
Continuous current.
Yes, sir. Means you take an alpha greater than 30 degree or 60 degree. You take that case as discontinuous conduction, and other cases as continuous.
Now one thing is, if you check the discontinuous conduction, na, your output voltage decreases. Definitely, na, discontinuous means it is having somewhat zero intervals.
Yes, sir.
Right. So your output voltage will be reduced, and continuous conduction means you will be getting more output voltage.
Okay.
Right. So means where you can say that for the loads, okay. Generally we prefer the continuous only. Yeah. Let me tell you, because this type of waveform, which is having a zero intervals, right? That may cause overpressure to your other filters, that whatever we are using at the end of the circuitry.
Yes,
so that will cause overstress for those filter elements. So it is better to always our try is to give the constant voltage, right? But whether we are getting the constant voltage, no. So that's why we're putting
No.
the additional things, just like a filter and those things. Okay.
Oh, yes, okay. Okay, sir. Thank you. That's all.
Okay. Yes, next.
Hello, sir.
Yes, please.
Page number 109, sir.
109. Yes.
Please explain V0 waveform, sir, once again.
Okay. Yes. You can check at this instant we are firing T1.
Yes. At
Okay,
alpha
this is
equal 30 degrees.
Yes.
Alpha equal 30 degrees, sir.
Yeah, alpha 30 degree I am saying. Hello.
Hello, sir.
This is alpha 30 degree means what? This was like omega t is equal to pi by 3 means alpha equal to 0 for thyristor T1 na?
Yes, sir.
So alpha 30 degree means after this instant I need to add 30 degree. So that's why it is a alpha for thyristor T1 na, this is.
Yes, sir.
Okay. Next, what is happening? You can check at this instant T1 is turning on.
Yes, sir.
But if you check, we are having the circuitry like this, where upper group consists of the controlled switches, lower group consists of the uncontrolled switches.
Yes, sir.
Now, yes, we can control the thyristors, which thyristor can be turned on, that we can decide by applying the gate signal.
Yes, sir.
But whether which diode will be in the conduction mode, whether that can we decide? No, that will depend on which line voltage is maximum. Na?
Yes, sir.
That respective diode will turn on. So now you can check at this instant, our thyristor T1 is triggered. So corresponding to this point, if you check at the line voltage side, which voltage is maximum? VAB, na? Yes or no?
Yes, sir.
So now if I turn on the thyristor, definitely T1 is connected to phase A.
Yes, sir.
So if VAB is maximum means along with the T1, which diode should be in a conduction mode?
D6, sir.
D6. So that's what T1 D6 conduct.
Yes,
So in the output, we are getting which waveform? VAB. So you can check here. We are getting the VAB waveform from this instant. Sorry, here not here. From this instant, I am getting the VAB waveform.
Yes, sir.
After that, it is similar here, na?
Yes, sir.
Now you can check after this instant what is happening. That is important. After this instant, VAB is less than that of VAC, na?
Yes, sir.
So VAC means which voltage? VA. Here it is VC. Initially it was VAB, na? Now it is VAC greater.
Okay.
So VAC means terminal A is again connected to T1. Our T1 is in on state only, na?
Yes, sir.
So now whether the diode D6 will conduct or diode D2 will conduct?
D2 will conduct, sir.
Definitely D2 will conduct, because yes, VAC is greater voltage than that of VAB now.
Yes,
So that's why T1 D2 conduct. So when T1 D2 conduct, in the output we will be getting VAC, na?
Yes, sir.
So you can check here, we are having the VAC waveform here in the output.
Okay.
But next you can check till this instant it is like a VAC is a high peak
Yes, sir.
value. But at this instant you can check after this instant VAC is lesser and VBC is more, na?
Yes, sir.
But in order to get the VBC, you can check, in order to get the VBC in the output, definitely your T3 should be in on state, na?
Yes, sir.
But whether T3 is in on state at this instant, no, T3 is fired here, na?
At the,
So means till this instant, which two devices will be in a conduction mode? T1 and your
T1 and D2. sir.
D2. So that's why we're getting output is VAC.
Yes, sir.
After that, again, when T3 conducts, along T3, we'll be getting VBC output voltage. So that respective diode will conduct, right?
Okay, sir.
So this type of pulses we're getting. Okay.
Sir, page number 96, sir.
96. Yes.
You drawn a IA waveform, no, sir?
Huh.
For IB and IC also same waveform, sir, we get.
No, only shifted waveforms. Definitely IB and IC also will be consisting of 120 positive, 120 negative pulse.
Okay, sir.
But that will not occur at the same instant, na? From which instant to which instant IB is a non-zero, that will be decided by, yes, which devices are conducting, na? You
Yes,
can
sir.
check, IB is here. This current is IB, na?
Yes, sir.
And to the B, we are having T3 and T6 connected.
T6, T2,
T3
sir.
and T6, na?
Yes, sir.
So you can check when T3 is IT3 is a positive And when IT6 is positive, what will happen to IB? When IT3 is positive, that is when thyristor T3 is in a conduction mode, IB will be positive.
Yes, sir.
Because T3 allows current in only upward direction.
Upward.
T6 also allows current in only upward direction.
Direction.
So when T3 conducts, IB is positive. When T6 conducts, IB is negative. So you can check here from this, we are having during which interval T3 is in a conduction mode, during which interval T6, yes, T3 and T6. Yes, T6 is in a conduction mode. You can check here. Here it is a T6 in a conduction mode from this point till this point.
Yes, sir.
So during this interval only, we'll be having a negative pulse for thyristor for IB.
Okay, sir.
And positive pulse will be appearing when T3 is in a
sir.
conduction mode. So T3 is here, and here it is also T3, means for this interval and from this interval, right?
Okay.
So we'll be getting the same kind of thing, but only shifted waveforms,
Okay, sir.
right? Okay.
Sir,
Yes, please.
sir, once explain three-phase controlled RL load, sir. Morning class.
Morning class. Okay. Three-phase half wave, na?
Yes, sir. RL load, sir.
Yes, I'm checking. Yes, this one.
Yes, sir. Waveform.
Okay. Yes.
Yes, sir.
So here
One second.
for alpha less than 30 degree, na?
Both waveforms, sir. What is the difference?
Okay, yes. So alpha less than 30 degree. You can check alpha 0 for thyristor T1 means it is pi by 6.
Yes, sir.
For thyristor T2, alpha 0 means 5 pi by 6.
Yes, sir.
For thyristor T3, alpha 0 means 9 pi by 6, right?
Yes, sir.
So now we are keeping alpha less than 30 degree, but it is a non-zero. So
Yes,
that's
sir.
why you can check pi by 6 to pi by 3. What is the angle difference? 30 degree.
30 degrees.
So this angle difference is 30 degree. So here I have between these two, I have selected one point, and here I am applying the gate push to thyristor T1. So now here you can check alpha means this angle, na?
Yes,
This
sir.
is alpha, right? Now, so here I am applying gate push to thyristor T1. At this instant, I am applying gate push to thyristor T2. Similarly here, thyristor T3. Okay.
Okay, sir.
Next, when T1 is triggered in a continuous cycle, when T1 is triggered, right? So when T1 is triggered, so what will happen? You can check this circuit diagram. When T1 is in a conduction mode, na, output voltage, how the current will flow? VAN, T1 load, and again back to the VAN. In this loop, current will flow.
Yes,
So
sir.
V0 is equal to VAN only,
Yes, sir.
right?
Yes, sir.
Audible? Okay.
Yes, sir. I'm
So
okay,
you
sir.
can apply KVL to this loop. It is a plus VN minus V0 is equal to 0. Okay. So you will be
Okay.
getting V0 is equal to VAN, right? So V0 is equal to VN. So here, that's why when T1 is triggered, output voltage is VAN. Same as that of this thing. At this instant, we are triggering thyristor T2, na?
Yes, sir.
Once T2 turns on, then what will happen? Once T2 turns on, your T1 will turn off. How it will turn off? Because when T2 turns on, na, it is T2 is acting as a short circuit, na?
Yes, sir.
So that's why here you can check this voltage is VBN. This voltage is also VBN. Here it is also VBN, na?
Yes, sir.
The voltage across thyristor T1 is VAN minus VBN. So you can
Yes,
check
sir.
at the instant of applying gate pulse to thyristor T2. Okay. At this instant, what is a VAN? It is a negative.
Yes, sir.
No, at this instant, right? So just after this 5 by 6, okay, it is a negative, right?
Yes, sir.
Estimate this point is like this, somewhat here. Okay, here, somewhat here. It is not negative, it is positive only. VAN is less than VBN, na?
Yes, sir.
At this triggering instant, VAN is less than VBN. So VAN is less than VBN means your thyristor anode voltage is less than cathode voltage. So thyristor T1 will turn off.
Turn off.
Once T1 turns off, what will happen? Current will flow through T2 only.
Yes, sir.
So in this loop, current will flow. So what is V0? V0 is equal to VBN. So that's why you can
VBN.
say in the output we are getting directly VBN here. Initially it was VN only till this instant. At this instant T2 conduction. That's why suddenly the output voltage will increase, na, from VN to VBN. So that's why sudden increase is there. After that, output voltage will be like a VBN only till we fire the thyristor T3. Once T3 is triggered, your T2 will turn off. So that's why output voltage is again VCN. So we'll be getting this type of 3 pulses, right?
Okay, sir. For in greater than alpha, then why are getting negative voltage, sir?
Because you can check greater than alpha means, yes, this one.
Yes, sir.
Pi by 6 means alpha 0 na? For thyristor T1.
Yes, sir.
Suppose alpha greater than 30 degree means pi by 6 to pi by 3, which is a 30 degree. Means after this instant, I am applying the gate pulse na. So I am considering at this instant I applied the gate pulse to thyristor T1. So before this thyristor T1, which thyristor in a continuous cycle, which thyristor will be in a conduction mode? T3. Before T1, which thyristor will be in a conduction mode? T3 na?
T3, sir.
When T3 is in a conduction mode, output voltage will be like a VCN.
Yes, sir.
So you can check 0 to pi by 3 VCN is like a decreasing at pi by 3 it reaches 0 value.
Yes, sir.
And after that it is a negative na VCN.
Yes, sir.
Why it is negative? Because VCN is negative, so that's why V0 is negative. But the thing happening here is we're having a REL load na.
Yes, sir.
So in the REL load, it is like even after VCN is 0 and after that VCN is negative, our inductor was like releasing the energy, right?
Yes, sir.
Through thyristor T3. So when inductor releases energy through thyristor T3, V0 is like your VCN only. So VCN is negative,
Yes,
V0 is also negative, right?
Yes, sir.
Right? This is for REL load only, but for R load, you will not get the negative voltage, right?
Yes, sir.
Okay.
Because in the absence of inductor, we will get continuous, sir.
Because of?
Absence of inductor.
Yes, due to the inductor, we are getting the continuous conduction.
Sir, for in control case, we have get the 0 voltage, no, sir. In evening class for R load, we have get for negative voltage, no, sir. For R is equal to. That is for fully wave control rectifier.
Okay. Yes. Here. This one?
Yes, sir. Alpha greater than 60.
Where we are having negative voltage? That is for REL load, we got negative.
Yes, sir. 0 voltage I have said, sir.
Yes, 0 voltage we are getting. This is for R load, na?
Yes, sir.
Just now, whatever we discussed previous to this, that was for REL load. You can check 3-phase half wave control rectifier for R load. You will not get the negative voltage.
In that case, you will get positive only, so we will not get 0, no, sir.
When?
Why you are getting here 0?
We are getting the 0, na? In the case of half wave also. You can check. This is 0 pulse is there na for alpha greater than 30 degree.
Okay.
This is for R load that we discussed in the morning session. This is R load na. For R load we are getting two things. One is alpha less than 30 degree. That is a continuous waveform, right?
Yes, sir.
Alpha greater than 30 degree. That is a discontinuous waveform, right?
Yes, sir.
So keep it in mind. If the load is resistive na, there
Yes,
for a half wave control rectifier, it is like alpha less than 30, alpha greater than 30. For less than 30, it is a continuous conduction. For greater than 30, it is a discontinuous conduction.
Discontinuous.
Right?
Yes, sir.
Similarly, for your 3-phase full wave control rectifier also, right? If we are having a alpha less than 60 degree continuous conduction, alpha greater than 60 degree discontinuous conduction, but here that discontinuous means V0 will be having a 0 interval, as well as V0, right? But for REL load, we are having only continuous conduction.
Okay, sir.
Right? Okay.
Sir, another one, sir, in 106 page, sir.
106. Yes.
106, sir.
Yes, this is 106.
I think 107, sir. 105, 105.
107.
105, sir.
105. Okay.
Here, how we got IA RMS value, sir? I0 into root 2 by 3.
Okay. That I have written here. You can check. IA waveform we are having, na?
Yes, sir.
This is IA waveform.
Yes, sir.
So you can find the IA RMS for this waveform. You will be getting IA into root 2 by 3. It is
Okay,
simply
had
what the
written
thing
that.
is. It is like a 120-degree positive, 120-degree negative.
Sir?
120-degree positive, na? This is 120-degree. This is also 120-degree.
Yes, sir.
Here it is 120. Here it is 120.
120.
So total non-zero is 240.
Yes, sir.
So how we find the IRMS? It is like 1 by 2 pi, right?
Yes, sir.
Integration from pi by 3 plus alpha to
Pi
pi
by
plus alpha, plus integration from 4 pi by 3 plus alpha to 2 pi plus
2
alpha,
plus alpha.
right?
Yes, sir.
It is a I0
Yes,
square and minus I0 square. Minus I0 square is again I0 square.
okay.
You can simplify. You will be getting under root 2 by 3, right? Keep it in
Okay,
mind. If it is 240 degree like this, 120 plus 120, your I0 RMS will be always root 2 by 3 into I0. Okay, but that should be the constant current here. Then and only then that is true. Okay.
Okay, sir. That's it, sir. Thank you, sir.
Okay.
Hello, sir.
Yes.
I have doubt, sir. I asked on the WhatsApp, sir, about voltage drop across resistor, sir.
Okay. Yes, please. Now, will you please elaborate what is your doubt?
Sir, actually, I am not getting while actually, sir, while we calculating the power, we take across resistor, we take the RMS value of the voltage and
Voltage
RMS
into
value of the
RMS
current.
value.
Yes, sir. Sir, like that, sir, I am not getting. Suppose we have to calculate the voltage drop across that resistor. Then we have to take the average value of current flowing through that resistor or RMS value of current flowing that resistor. Because, sir, some their average value and RMS values are different now. So in that case, sir,
Yes.
I'm not getting, sir.
No. The thing is whether you want the average voltage across resistor or RMS voltage across resistor, that decides whether you are going to use the I0 RMS or I0 RMS or I0 average.
Okay,
If we
okay. Means,
want
sir,
the average voltage across resistor, then we need to go
yes.
for I0 average into R. If we want RMS
Okay.
voltage across resistor, then that should be I0 RMS into R.
Okay. Then, sir, that voltage drop will be different, na, sir. Means RMS voltage drop
Yes,
and
yes.
average voltage.
No, but the thing is, for which purpose you are finding the voltage drop? Whether it is for, suppose,
Yes, sir.
we are having a RE kind of load, na?
Yes, sir.
In the
Yes.
RE load, what we wrote generally, KVL application, KVL equation, V0 is equal to I0 into R plus E, na?
Yes, sir.
So while calculating the V0 average, generally we wrote that I0 is nothing but I0 average into R plus E, we wrote, na?
Yes, sir.
If at the left hand side we are having V0 average, then only we are writing the I0 average into R. But the thing is, you can check here. Let me show here. Yes. Suppose we are having a RE load and V0 is equal to what? RE into I0 plus E, na?
Yes,
This I into R0 is nothing but your VR.
yes,
This
sir.
suppose
Voltage across.
if I want the V0 average, then
Yes, sir.
I can write VR average plus E, na?
Yes,
Because
sir.
average voltage
We
of
can
the
write.
E is E only, right?
Yes, sir. Yes.
So now here it is. Yes, it is clear that I require the average voltage across resistor. So that's why I am writing I0 average into R, na?
Yes, sir.
Is this clear?
Yes, sir.
So
Yes,
unless
sir.
and until you specify whether you require the average voltage or RMS voltage, we cannot
Okay.
comment which current we need to put.
Okay, sir. Okay, sir. Means, sir, we have to find average voltage, then we have to take the current is average. And suppose here, sir,
Average,
we
yes,
want to, okay. And sir, suppose in that case also we want to find the RMS, sir. In that case, sir, RMS value of the E will be, sir, E also. E. And sir, and here we have to take just IRMS like that.
But generally, where you require that V0 RMS, that V0 RMS
Sir,
we calculate from the waveform, na?
okay, sir.
That is
Okay,
it.
sir. Then. Okay. Got it, sir. Yeah. Thank you, sir.
Yes, please.
Hello sir, good evening.
हाँ सलमान खान जी बोलिए. Good evening.
Sir, I have heard that how triggering takes place, sir.
How?
We are three thyristors. How
Please,
automatic?
please, will you please speak a bit louder?
Sir, how this automatic triggering takes place, sir, of thyristors?
How the automatic
triggering?
Ah.
The one thyristor triggered means it doesn't depend on supply directly, na sir.
Once thyristor triggered, then
how other thyristor triggers after some interval automatically?
Okay. Means you are saying in practical case how we are controlling the triggering, how we are providing the gate pulses.
Yes sir.
Okay. Actually, for that we are using the circuitry. We are not manually triggering. So for that I need to use your controllers, microcontrollers we are having, na?
Yes sir.
In that I need to, because microcontroller is like your smart device. In that I am going to write a program. Okay. And accordingly I am going to that switch is there na in your gate cathode circuit. Okay. Because unless and until you circulate the gate current, your device will not turn on.
Right,
and
sir.
whatever the switch we are going to connect in the gate cathode circuit, right? That switch should be controlled, okay, by your program.
Okay, sir.
Right? Means again, it is with the help of your relay circuit. That relay circuit will help your switch to turn on and those things. Okay. So that is the additional part. Means that is actually while designing the system, what requires. Okay. That is your question.
Yes, sir. That was
right. Because manually we cannot apply the gate signal every time, and we are having very small time interval.
Yes, sir.
You can check for 50
speed is
degree.
very high.
If at omega t is equal to alpha m, suppose we are having only single phase full wave control rectifier. Again, if I consider, suppose I am having a 4 thyristors. At alpha I am triggering T1 and T2. At pi plus alpha I need to trigger T3 and T4 na?
Right, sir. Right.
But what is the difference between that triggering difference, time difference between the triggering of T1, T2 and T3, T4? Very small. Only pi radian we are having. And if you consider our Indian frequency is 50 hertz, okay, so that corresponding to pi radian means it is like we are having very 10 millisecond time we are having, right?
Yes, sir. Right.
So in a 10 millisecond I need to turn on, okay?
Yeah, yes, sir.
Same thing. So for that we need to use the intelligent devices, right? Okay.
Right.
Okay,
sir. Thank you.
Yes. Yes, please. Yes, tomorrow I will give the 3-phase controlled tricks, okay? Yes. Pratik Bhosle, okay. Circle holiday for dono, okay. Okay, right? So we'll stop here. Tomorrow we'll be discussing about the dual converter and some numericals related to the rectifier, right? And after that we'll be starting the DC to DC converters, right? Okay. Thank you. Thanks to all of you.
Thank you, sir. Good night.
Yes. Good night. Good night.